like contrastive divergence is a method, whereas KL divergence is a metric. So divergence is like an operator that takes in two probability distributions as an input, and its output is a number that quantifies kind of how different those distributions are from each other. Whereas contrastive divergence is a way of approximating a distribution, like a way of training a probabilistic model to match a distribution, as I understand it.
Yeah, yeah. I think yeah. So KO divergence is like the same as like relative entropy.
Yes.
It's a bit more descriptive to call it that. That's what I've been noting it in my head as.
Yeah.
Yeah,
Right.
it's
It's that. Yeah.
it's not symmetric either, so it's not quite a metric.
Right. That's true. Yeah. Yeah.
I did read that there's you can make like a symmetrized version of it, um, that becomes a metric, which is kinda I'm a geometer, that's my
Okay. Cool.
background, I got my PhD in math, so I'm very interested in this stuff.
Yeah. 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 They're right. So there's symmetrized versions. I'm still not sure if it satisfies like the triangle inequality. I don't know. Maybe it does. I honestly don't remember. But yeah, I'm more kind of metric in the broader sense of just like a way of measuring something, kind of evaluating something. But yeah, totally agree. It's not strictly speaking a metric in the mathematical sense. Yeah. Um, well, all right. So why don't we kind of get started? So just with like the idea of EBMs. So I guess I'll just say a few things about how I kind of understood what he's saying here. In just this first section, 24.1. Also, let me know if anyone doesn't have access to the book. Just let me know or send a message in the chat. But so he first starts off by saying EBM is it's really just this simple formula here, equation 24.1 together with 24.2, where instead of like trying to specify this probability distribution p theta of x, like instead of trying to specify that directly as some function, you describe this function e theta of x, and then you exponentiate that. You do e to the minus e theta of x, and then you need to compute this normalization factor z. So something really important to notice here, just at the surface level, is that there's two kind of important parameters. There's theta and there's x. So x is like the variable that when we observe data, our data point will be in the space of x. Our data point will be in x. And then theta are like, these are the parameters that we are varying to try to somehow model the distribution of the data. And basically, like the fundamental problem being solved here is that we get a bunch of samples from a distribution, and then we want to be able to learn a way of producing more samples from the same distribution, which is kind of like the classic problem of like generative AI, right? Like you have a bunch of image data from the internet, and you want to be able to learn a way of producing new samples from that distribution that look like plausible images you might kind of find on the internet. And right off the bat here, we see there's this thing that's kind of problematic, which is that this partition function, where the normalization factor z involves an integral over, well, ostensibly the integral goes off to infinity in every direction, and it's going to be like in general like a really high dimensional space, right? So it's not like something you can do by numerically integrating using like a Riemann integral or something like that. So that's just kind of another important thing to notice. But yeah, I don't know. Any thoughts on that part of the book? I'm going to keep inviting people to speak if anyone wants to come up.
I'm trying to set up my to help me kind of muddle my way through this a bit. But I noticed that, and I'm seeing if in fear of PDM do not usually make any Markov or something. Um, and so evaluating the integral is nearly intractable. So I'm trying to parse that. How would one define a Markov?
Yeah, so I'm guessing that probably he gives like a definition somewhere else in the book that I'm not sure exactly how he's defining it. But in general, like what Markov processes model is a collection of random variables such that are ordered, right? So you have like X1, X2, X3, and these are all different random variables. And there's kind of this ordering that you could think of as like time, like X1 is the first one you observe, then X2 is the second one. And they're not independent random variables. But the important thing is that if you know Xn, then you know all that can be known about Xn plus one. In other words, knowing X1 or X2 or all of the previous X's before Xn, that doesn't give you any additional information than if you just know Xn, that gives you everything you need to know. So another way of saying that is that for all j greater than I, Xj is conditionally independent on, k less than I. So sorry, it's kind of a mouthful, but you could time ordering thing, but yeah.
Yeah. So could you, would you be able to, I'm like trying to map this in my head. Is there like a good example of something that is a Markov proper or could be described?
Yeah, a great example was just a random walk. So let's say that I'm standing in my room and I flip a coin, and if it comes up heads, I take a step to the left, and if it comes up tails, I take a step to the right. And I always take a step of the same distance, say 2 feet exactly. And the important thing is that like if after my 10th step, let's say that I'm 10 feet to the right of where I started, okay? And somebody asks, what's the probability that on the 11th step, you're 12 feet to the right of where you started or 8 feet to the right of where you started? And the point is that knowing where I was on the previous steps doesn't help you make that prediction. The only thing that'll help you make that prediction is knowing where I am on the 10th step. It doesn't give you a more accurate prediction.
So this is like the same thing as the memoryless property of distributions, just applying to like state transitions.
Yeah, absolutely. And actually, so yeah, when I was in grad school and working on like quantum thermo stuff, the term Markovian gets thrown around a lot, but also the term memoryless, and they mean the exact same thing. Markovian, memoryless, it means, same exact thing. So yeah, that's a good way of putting it.
And then my follow-up is, so presumably the inverse of this is a non-Markovian proper, which means I must know all of the previous Xn values in order to efficiently predict my correct. Do I have that one correct?
Yeah, exactly. Or in other words, like knowing the previous time steps would give you more information about, where you'll be at the next time step. Yeah.
Okay, got it. And then, so random walk is a good Markov process. What's a non-Markovian?
Well, I guess, one easy kind of lazy answer is almost anything you'll see in the real world, right? Like people often use like a Markov, as a textbook example of a Markov process that's an idealization is like the weather. So like if you look at like the weather in some area, maybe like a third of the time it's rainy, a third of the time it's sunny, a third of the time it's cloudy or something. But maybe there's some correlation where if you have a rainy day, it's more likely the next day will be cloudy or something. So you can model that as a Markov process, but realistically, it's probably not a Markov process in that there are kind of more correlations you could take advantage of. If you look further back in time, that might tell you more about like the weather on the next day or something like that.
Yeah. So my rabbit hole has been there's tangentially related to Markovian, non-Markovian processes, and then the stochastic proper in relation to a Markovian for non-Markovian process. What would be a good example of it? Relating, I think it is.
Yeah. So I guess like the blanket term of stochastic process is like very broad, and it kind of covers. It basically means a kind of probability distribution, but where the stochastic processes can also just be random variables like let's say a vector of size n could be thought of as a stochastic process, but usually it has to do with random functions. So like if you want to describe a random variable where the variable is actually a function, like say the position of a particle as a function of time, this is like kind of a continuous function. And you can, it kind of generalizes the idea of a probability distribution because it's like a distribution over functions. But not all like there, like also the random walk example where I was flipping a coin and taking one step, and that's kind of a discrete time. That's also a stochastic process. So a stochastic process is kind of general, but yeah. So some have like a Markov property, and some don't. An example, one that has a Markov property is like if you think of that random walk again, and you take a certain limit. So let's say that I'm flipping a coin, and every 1 second I'm taking a step of 1 foot. And then somebody else is flipping a coin, and every half a second they're taking a step of half a foot. And there's someone else who it's a quarter of a second and a quarter of a foot. And you kind of keep going on and taking the limit. And if you take that limit, you get Brownian motion, which is like a continuous function of time and looks, like a very kind of badly behaved, noisy function.
Got it. And then the half second is where we get the Planck. Do I have that one?
No, I don't see the connection to Planck's constant actually. Yeah, well, so I think though, yeah, to get Planck's constant, you have to involve, physics in some way. Whereas like the level we're talking about now is kind of a mathematical idealization that doesn't really care about any, real world physics, I guess.
Oh, interesting. Okay, so it's the stochasticity, Markovian, non-Markovian would be the kind of differentiated over into quantum physics, and then if we want to go over to Planck's constant, then we have to go get in classical physics.
Well, I mean, I guess you can get Planck's constant by doing a quantum treatment for sure. And Planck's constant is definitely going to be very important in quantum mechanics. I mean, in a sense, you can have Planck's constant in classical physics if you're kind of talking about like semi-classical theories. Like in other words, before they had the full framework of quantum physics, they still knew about Planck's constant, I guess.
Right.
But you're going to need to involve some kind of physics to get a Planck's constant.
Yeah. Okay. And then these processes don't necessarily need to involve physics because they're just probabilistic.
Yeah, exactly. Like if you think about like I can simulate this process on my computer, and the computer it doesn't even have to have units, right? Like I don't have to say I'm stepping 1 foot to the left or the right. I can just say my position is changing by 1. So if you have a system where there's no units, you're not going to have like these physical quantities like point constants, etc. So this is on this higher mathematical plane, I guess, at this point. But yeah.
Got it.
I do kind of think of Planck's constant as almost like reality's resolution or something like that. Like it's like the smallest, some kind of smallest quantum of something. So it's kind of like defining what a bit is in reality or something like that.
Right. Yeah. Yeah. Actually, I guess that is an interesting perspective in that so the question, the original question was is in this limit of taking smaller intervals of time and smaller steps, is that where Planck's constant comes in? And the comment you made just now made me think, well, maybe in a way that is a fair thing to say. And that if you look at real Brownian motion, you try to trace that trajectory, it kind of looks like this fractal that no matter how small, whatever length scale you look at it, it still looks like spiky and badly behaved. But I mean, we do know that, the position isn't really well defined below the Planck length, right? So it can't really be like that forever. It's when you look at it at some scale, you have to think of it as a wave function. You can't think of it as this spiky trajectory, but yeah.
Yeah, I almost think in your coin flip example, it's if you were simulating that process on a computer, you can only have finitely many players in the game, and maybe Planck's constant in that game is kind of the step size of the smallest one, right? Like the one who's taking the smallest steps or something like that.
Yeah, I think that's basically right. You could think, yeah, if you're simulating it on a computer and you want to map that simulation to something that happens in real space, then you probably shouldn't be using step sizes smaller than the Planck length because your results are going to be kind of nonsense. So, yeah. Okay, cool. Yeah, I think there's a lot of question already. I guess I didn't actually, I didn't totally answer the question, which was why does this Markov property matter, actually? I think that, and I don't actually know for sure, but I think that basically one way it might matter is that if you did make this assumption, this kind of makes the distribution a lot simpler in a way because you've assumed this conditional independence. And maybe if you make that assumption, these integrals, like the integral in equation 24.2, actually can be simplified a lot using some kind of trick, basically. I think that's what that there's some mathematical trick to simplify that integral if you have a Markov property.
So making that Markov assumption is we're going to determine that this is either Markovian or non-Markovian. We do that, then we can simplify heavily. But if we just say like we're gonna abstract that away for now, so we're not gonna make any assumptions about the Markoviness of this. This allows us to do this sort of more complex study of the thing that we're.
Yeah, exactly right. And importantly, like the Markov assumption also depends on like having some natural way to order the different random variables you have. But like that doesn't sometimes it doesn't really make sense to even do that at all. Like for example, if your random variables are the intensities of different pixels in an image, like it's not obvious what is the right way to order those variables or something. Right. Whereas with time series data, you could at least say there is like some ordering, but yeah, so there's not always a good way to do that, basically, I think is the idea.
Got it. Cool.
Okay. Cool. So yeah, I think we talked about this. Yeah, this a good amount in the introduction. So the next section was this like 224.1.1 product of experts. And when I was thinking about this, I think that the clearest way of thinking about it to me is that there is by kind of comparing it to a mixture of experts. And you can think of like the mixture of experts as like an or kind of, and the product of experts as like an and. And so like, can you explain a little more what I mean by that? Like, let's say I have two different distributions. Here he calls them P1 and P2. And P1 kind of describes objects that have a certain property, and P2 describes objects that have another property. Meaning that if I draw a typical sample from P1, that would be an object that has the first property. If I draw a typical sample from P2, that would be an object that has the second property. And one thing I could do is I could draw half of my samples from P1 and the other half of my samples from P2, which is basically a mixture of experts. I mean, it's to be precise, a mixture of experts would be you would randomly decide whether to draw from P1 or from P2. But that's a mixture of experts. And that if I do that, I'll get objects that either have property P1 or have property P2, but not like objects that they don't have to have both. Whereas the product of experts is I multiply the two together, P1 times P2. And if I draw samples from that distribution, I'll get objects that have both properties, kind of, if that makes sense.
Do all would think I'm thinking like, do all of those objects necessarily have some amount of 1 and 2 because of how we are sampling them? But I think the answer to that is no. It's either 1 or 2 or a probability distribution over 1 and 2, right?
Yeah, I mean, I guess that's a good question. Like, well, so first of all, there's always the possibility that like you'll get a sample that is unlikely that you're unlikely to get, right? So like even if if you grab a random person from the population, you could get a person who's 9 feet tall. It's unlikely. But I think the idea is that like the typical samples that you'll get from this product of experts from this like equate from this distribution 24.3, the typical samples you'll get are things that have both properties P1 and P2. But can to varying extents, I guess.
I have like a model architecture idea, and I've been thinking about this a lot for like the last year or 7. But this idea of product of experts I really like, because the way I've been thinking about this model architecture I've been thinking about is as like an entanglement of experts. And I almost think of it as like a group of people who are voting on whether or not they think something's true. And because they're experts, some of them will have strong opinions about the things they know about, right? And then like ideally, if one of the experts doesn't know the answer to the question, they just like express their uncertainty or something. And so when you take the product of probabilities of across experts, I guess like if one of them is very confident, that like pushes up that product of probabilities, and then everyone else is just kind of expressing uncertainty, and you're hoping that your model is like learning, that your experts are basically like learning how to vote when their opinion is relevant or something.
Right. Yeah, actually, I like the idea. Like the way you're describing it is kind of like picturing like who are these experts? Like almost you can imagine they're gathered there around the table. And I really like that picture because it kind of brings to life one aspect of the like the mixture of experts versus the product of experts, which is that in the mixture of experts, everyone kind of has their say and everyone has a vote, but nobody has like a veto power. Like no one can say, okay, this is not a sample we will allow. Okay. But in the product of experts, everyone has a veto power because if any one of those experts assigns a probability of 0, then that thing has a probability of 0. So you can always think it was like the House versus the Senate, right? Like everyone there's a filibuster in the Senate. You have this. Everyone is very powerful because all of these experts can veto something basically. So that's another way.
Literally. That's a great analogy, actually.
The mapping it like one very like orderly. We're gonna take your opinion, then your opinion, and the other one is just everybody's shouting at each other.
Yeah.
So one of the things that I've been thinking about a lot, like especially this last week, is that in mixture of experts models like this, or let's talk about product of experts. What you really want is a model in which the experts are kind of like maximally differentiated from one another. And I feel like the way that you do this is by like maximizing some kind of entropy.
Interesting. Right.
This is like the thing I've been like, I can't stop thinking about this. This is all I've thought about for like the last like 3 weeks or so, is that you want to do something like simultaneously maximize entropy and minimize cross entropy or something like this, where you're trying to tell the experts like, hey, you guys should all be like doubtful of your own opinion. But speak up when you have a strong opinion, either way.
I see. Yeah, that kind of makes sense. I think probably like the more traditional approach is just say the different experts are just going to be trained on different data. And that's how we're going to ensure that they all have their unique, like kind of perspective, I guess. But also you're saying it's interesting because like you could think about it like, well, let's say that we're just going to train them all on one single stream of data. And how do we make sure that they all learn different things from it? And it's kind of suggesting like maybe there's some coordination that they can do to like, yeah, using information theory or entropy to make sure that everyone kind of learns a different aspect of the problem or something.
I think there's an idea related to this that Yann LeCun has a paper that I really like, and it's about this idea called maximum manifold capacity representations. And I didn't realize until like the last week or so that there's a connection between these two ideas, but like basically it's like a multi-view self-supervised learning technique where the different views of the input are basically being mapped onto some sphere. And when you train on like a batch of examples, you basically get a bunch of, for each example, you get a bunch of points on a sphere, and you take their centroids for each example, and then you're basically trying to spread out the centroids as much as possible. So you're trying to like make sure that the different views of the input end up like on different parts of this sphere. And I have this feeling that this is equivalent to basically training a mixture of experts where you're having it maximally distinguish their like embedding representations of the input, or however you want to think about it. If anyone wants to collaborate more closely on this, hit me up after this.
Who's that?
This is Bill Carr.
Yeah, that what it made me think of engine, the one there where it's like we took it and we smashed it together with
Yeah, that does sound cool. Like it reminds me of like the techniques people use to like prevent kind of like mode collapse and stuff. Like if you have like an embedding model and you don't want everything to get embedded to the same point and stuff. So, but yeah, I never thought about that, like techniques like that in the context of mixture of experts or product of experts. So that does sound interesting. Yeah. So just I guess the other thing I wanted to say just on the topic of mixture of experts is this important thing, which is in equation 24.4, because here he's starting to make an argument for like why use energy-based models. I mean, he's already said maybe one or two things, but this is a kind of a nice reason to care about energy-based models, is that they make products of experts really easy to describe Because if you think about, if you look at equation 24.1 again, and if I had two terms of that form, like if I had an energy E1 and an energy E2, and then I did e to the minus E1, and then I also did e to the minus E2, and I multiply those together, then what I'm going to get is that I'm going to get e to the minus E1 minus E2, right? So they just get added together. And so that's what he's saying here in equation 24.4 is that in energy-based models, you can add together energies instead of multiplying together the probability densities. And so that's going to be something that's like more well-behaved numerically. For example, adding together a bunch of things is better than multiplying together a bunch of things. So that's kind of a nice way to think about the utility of like energy-based models, I think.
Yeah, and that actually, I can't help but feel like there's some direct connection between that idea and this maximum manifold capacity thing, where you're taking these centroids, like you're like averaging things over a sphere, so you end up on a point like inside the sphere, which could be close to the origin. And like basically the idea is that you're trying to spread them out, but like the key thing is that you can just take the different views of the input. It's essentially like multiple different embeddings of the input and just add them together to get kind of an aggregated embedding.
Oh, interesting. Okay.
Like same thing, right? Like if you take the gradient of a sum of energy functions, you're basically getting like an aggregated gradient of the different energy function.
Oh, okay. Right. Yeah, I see. Okay. So yeah, I'll have to read up on that. The manifold, maximum manifold capacity. 'Cause, yeah, I don't know anything about that actually, but it does sound interesting. Actually, let me see if I can find. Yeah, I think I found the paper, so I'll send the link of that into our group chat.
I just sent it to the group chat.
Okay, thanks.
There's multiple papers about that topic, but this particular one I sent that came out in June that has like Jan LeCun on it.
Okay,
That's the one that I'm kind of obsessed with that paper. It's a beautiful idea.
Completely obsession. I should mention here that when you are doing that aggregation, you're summing up those gradients. This is the same thing that we do with the Kolmogorov-Arnold network, where what we are doing is taking the multivariate function, and then we are treating that as the sum of a bunch of univariate. Way to shove in my univariate discussion once again. Perhaps that'll be useful to you when we're pouring.
Oh, were you on the CAN paper?
My hand.
I didn't know, or let's see. I don't actually know your name because
Or Warren is my government name.
I gotcha.
Hey, Max, with the product of experts, is there anything that would cause it to be anything other than a straight up product, or could it be weighted? Could the weightings be different of the experts?
So I think
I'm trying to find the equation.
Oh, interesting.
You can kind of just rescale the different energy functions.
Right. Yeah, you can do that. You can rescale, but does that actually change anything? Well, yeah, I guess it does. Like if you multiply the energy constant, if you multiply the energy function by something, that does kind of make it more sharp. But yeah, by definition, it is just these products like P1 times P2. So there's not, like it doesn't like, whereas in the mixture of experts, you could like have each one multiplied by a weight. But here, I think that if you wanted to, if you wanted to do something like that, the only freedom you have is to change the actual distributions themselves, like change P1 and P2. Yeah.
Okay, thanks.
Okay. Cool. Yeah, that's a good question though. So let's see. So, all right. So with the next thing, okay. So he talks a little about computational difficulties here. Let's see. Well, he doesn't actually say much at this point, but so then I guess the next section is on maximum likelihood trading, which is like kind of the most basic way of solving that fundamental problem of, just to restate the problem again, I'm given a bunch of samples from a distribution and I want to kind of find a way to fit. I come up with a model of a distribution that I think fits that source of data, and I want to fit that model so that I can produce new samples from the distribution. And so maximum likelihood trading is a way of solving that. problem. And the way you do it is, first of all, you instead of just like having one distribution, I have a family of distributions, right? Because I'm going to fit my distribution by choosing one from this family that best models the data. And that family is parameterized by this vector theta. So theta are, you can think of these as like the weights or the free parameters of my probabilistic model. And what the basic idea is equation 24.5, which is that this log likelihood is the log of the probability that my model assigns to the data. And then I'm like averaging it. What this averages is like I'm drawing samples from I'm looking at real samples of real observations from this source of data. And I'm asking how likely, if I were to ask my model, how likely would my model say I am to see this data point? But I'm looking at like kind of the log of that probability. So because there's a log here, one thing to notice is that it really penalizes kind of false claims of impossibility. So in other words, if my model says that the probability of seeing a person who's 8 feet tall is 0, my model says there are no people who are 8 feet tall. And then I see a person who's 8 feet tall, then that model is going to be really heavily penalized because it associated a very low probability with something that actually happened. So that's kind of the effect of the log here. Or one way of thinking about the effect of the log is to really penalize like false possibility claims, I think.
Yeah, and this, I feel like isn't this basically just like the same as kind of minimizing some kind of cross entropy or something?
Yeah, I think it might be. I'm actually not totally sure. But well, so it's equivalent to minimizing KL divergence actually, which is what he says in 24.6, that maximizing this log likelihood is the same as minimizing the KL divergence between the true data distribution and my kind of parameterized guess of the model of the distribution. But I think that's related. It's there. I don't remember exactly how it comes in, but there's the cross the KL divergence can be written in terms of cross entropy or something. I think so. So probably something. There's probably something there.
Yeah. I feel like one of the things I'm constantly frustrated about reading papers in ML is like there's so many similar concepts that many different people treat like slightly differently or use slightly different terminology for.
Yeah.
Howard, can I get a good definition from folks for KL divergence here?
Yeah.
Or go ahead. Go ahead.
You can go ahead.
Okay. Well, yeah. So I guess I was just gonna post the Wikipedia link because I think that. All right. So if you're in the art chat, so I'll just send that and it's because KL divergence it's been, I guess the idea has been around for a long time, but I feel like maybe like 10 or 15 years ago, people started to realize that it is kind of crops up everywhere. And it's become like this really kind of important and fundamental object of study in like a bunch of different fields. So like it's used all the time in physics, quantum information, machine learning now. So, but it's just it's a way of distinguishing, it's a way of measuring how different two probability distributions are from each other. And I think that one way of characterizing it is like if the real distribution of some random variable is p of x, and I think the distribution of that random variable is q of x, and I kind of, well, you can think about it in terms of like a game. Like if I'm playing a game where I'm trying to like guess, what p of x is or something, and I'm basing my guesses off of the distribution I think it is q, then like the tail divergence kind of quantifies like how much money I'll lose in that game or some sense. Or I guess another way is like if I try to compress a random variable, if I try to compress a random variable and I'm modeling that random variable with a distribution Q, but it actually comes from a distribution P, then the tail divergence kind of captures like how much information I waste by using the raw distribution to try to compress it or something like that.
Yeah, I liked on the Wikipedia page, I liked this one kind of down in the introduction context where it says the KL divergence is interpreted as the average difference of the number of bits required for encoding samples of P using a code optimized for Q rather than one optimized by P.
Yeah, I think that was a much better way of saying what I was trying to say. I think that's exactly the point. Yeah, that I was kind of circling around, which is, very, I can't really,
It's like a distance measure in bits. Like somehow, like how many bits of information would I have to change about my model, or I don't know, something like that.
yeah. Yeah. So that is a very nice way of putting it. Right. Yeah. Using a code optimized for P. How many extra bits do I use to encode samples from P? Using code optimized for Q. Yeah. But it is like just this thing that takes a long time to get intuition for. I think, like, I feel like working with these KL divergence things for a long time, and I've gotten kind of familiar with some of the mathematical tricks that you can use with them. But it's always been a little bit mysterious to me, to be honest. So I think, I can't quite have a perfect, understanding.
No, well, that's most of math for me. This does math thing to other math thing. Yeah, but it works in this context. And hopefully.
I was thinking a lot about KL divergence like earlier this year when I first, like at some point, sometime in the last year, I was like, okay, what the fuck is entropy actually? And I feel like if you start by reading about just what Shannon entropy is and interpreting it as like a number of bits of information, then KL divergence makes a little bit more sense. Like you're kind of taking a difference between two things that kind of look like entropy, but where you're like swapping out the log of one distribution with the log of the other distribution.
Right. Yeah.
Yeah, I went down that like same rabbit hole. It's quite an adventure.
Yeah. I feel like I got into this like thing where I was like, wait, okay, back when I was a physics major as an undergrad, I dropped my physics major, by the way, before I ever took like upper level thermo classes, but like I had always heard entropy described as disorder. And then you get into computer science and it's information. And this always seemed mysterious and weird to me.
Yeah.
I think I kind of get it now, but
Yeah. Yeah. I mean, I think that, the mystery of these things are part of what makes them kind of fun, especially, with the relative entropy or KL divergence, how it always seems to be like, a lot of times you can get a lot of insight into something when you put it in terms of KL divergence, and sometimes, the math, it just seems to work out perfectly, and it's kind of fun. Yeah.
Yeah, the way I think about KL divergence with respect to like the relative entropy is just like the number of steps that would be required to transform a reference distribution into a target distribution, and you can quantify the number of steps by bits, or maybe by the Planck constant.
I was going to go there.
Oh, that's interesting. Yeah, I hadn't thought about it that way before. Yeah. That's, like the number of steps you need. Huh. Cool.
Yeah, Lander's principle proposes like the bit energy equivalence based off the Planck's constant. So I kind of drew that analogy from there.
To do with non-Markovian KL.
Well, okay. So strictly speaking, KL divergence isn't Markovian or non-Markovian.
Right, because we don't make that assumption.
So being Markovian is a property of a stochastic process, or of like a sequence of random variables, whereas KL divergence is a way of comparing two probability distributions. So the property of being Markovian is something that applies to sequences of random variables, not to KL divergence.
Okay.
yeah, and I kind of think of like something that's non-Markovian, or like when we're thinking about something in the world as non-Markovian. This is like, okay, my own opinion, which is maybe dumb or whatever, but like, I think that like the universe probably is Markovian, but it's just that like any one observer in the universe doesn't have access to like most of the information in the universe, right? Like this is why you can't predict the weather, is there's just like too many other things going on that you would have had to have observed to actually like access the full Markov model. And so
Yeah, this is a great point that in general, like, I'm not sure if this is always true, but it's often true that like you can take a non-Markovian system, and if you make the state space larger and you include more of the environment, it becomes Markovian. But yes, something could be non-Markovian just because you're looking at a small part of the system, basically.
Here then, if I would like to transform from Markovian to non-Markovian, could I use a KL divergence in that case to measure like how much extra I would need to measure to get there if I could determine point A and point B?
That is interesting. I'm not 100% sure whether you can use because the way you would transform from Markovian to non-Markovian is by redefining your process, like redefining what your random variable is, redefining what your state is. So like, in other words, instead of like looking at, looking at a vector X, which has n components, maybe if I just look at the first two components of that vector, I get a non-Markovian process, where if I looked at the whole vector, I would have a Markovian process. But I'm not 100% sure if that is like, if that can be effectively quantified using KL divergence or something. I mean, for one thing, it's hard to do. It's hard because you have two distributions that are over different domains, right? So KL divergence is for distributions that are over the same domain. So it's not obvious how you would kind of compare the two using KL divergence, I guess.
An idea. Okay. As you were speaking, I was just thinking, well, if only we had construct a lot to trade space for time. Neural networks. That's exactly what you're doing there. That you're taking a sort of non-Markovian process that you're dealing with the universe that you don't have the hope to model completely. And what you're saying is that I am going to run this magical compression algorithm that, given a specification of what I'm trying to predict about non-Markovian process, is going to extract a fixed computation that I can run in a fixed amount of time, right? Because it's a fixed depth on certain number of matrix multiplications and so on and so forth. So you can build something like the guys from Grok accelerator company are doing with data flow, and lay out your models like that on hardware even. So you just traded space for time, and you found a pocket of universe that was important to you, right? Like it had evolutionary, it was evolutionarily adaptive, and you've trained a very generic function to predict it as much as it was possible given the data that you have. It's a very general model of learning how it works. And then once you have that object, then you can compare any distributions, right? Because all you have to do is to just do literally the distance between the weights if you train it that way. It is right. Because that object, the neural network, is the distribution. It is the generated model.
Okay, that's
But by the way, but the KL divergence does not represent the actual distance. It doesn't satisfy the metric measure. It's a true distribution, though, but it's not distance measure.
So I wonder if you could use Bhattacharya distance. That would be symmetric, and that has a distance measure, and that can be used to compare probability distributions, and has some interesting geometric properties. So I think there's a paper hiding with applied Bhattacharya distance and knowledge that gives you some nice properties because of symmetry.
Just sorry,
I remember it from my lectures on speech recognition. It's a measure of distance between probability distributions. That's actually a distance, and it's called BAT. 1 second.
Well, KL is not symmetric. So which one are you referring to?
I think I read that you can take. Ooh, okay, I see this. The Bhattacharya distance. Yeah, Bhattacharya. Bhattacharya. Yeah, it's an Indian name. It's a Bhattacharya. Yeah.
So it's like
exactly.
it's like negative log of the sum of the geometric means of the probabilities, like square root of p times q.
Yes, exactly. So because and you know why this is better and why this works, because probability is always geometric, right? When I realized like how does geometric
if you have a probability distribution, it can always be, it will always be possible to describe it geometrically.
So-
And it still does not satisfy triangle inequality.
What about
It's
the
still not a
distance?
metric. The Bhattacharya distance, yes, it's still not a metric. For the
Wikipedia.
But I think question I think the original question was like about quantifying the degree to which a process is not Markovian, right? And I'm not like the metric property of triangle inequality is definitely an interesting and important property, but it's it's not obvious to me whether it's like essential for quantifying that degree. I get so I guess one thing you could think to do, right? If I have any stochastic process, kind of think about like what's the closest Markovian process, which I'm not 100% sure like what the way of constructing that would be, but I think that there's probably a fairly simple way of doing it, which is, I mean, more or less, if you observe some sequence of data, like you can always kind of come up with a Markov process model of it by saying every time I see symbol A, how often is it followed by symbol B, right? Just by kind of computing these statistics, I can construct a representation of a Markov process tries to model that data. So like, for example, people for a long time tried to model the English language as a Markov process by saying like, how often is the word quick followed by the word brown, right? As it is in the the quick brown fox or whatever. Now, these like first order Markov models of English don't do very well, but you can still try to construct them. So you can take like any stochastic process and kind of find like the closest Markov process. And then I'm sure that there are a number of like, measures of discrepancy between probability distributions you could use to try to like compare them or something. But yeah, it's interesting. I never actually thought about that before. But so I did want to get back a little bit towards the topic of this chapter. This is a really good tangent. Actually, I was really happy to discuss this. But just to go back a little bit to the maximum likelihood training. So remember, the idea here was that we want to find the right values of these parameters theta, right? Like we have these parameters that describe a probability distribution. Like for example, if our distribution was a Gaussian, these parameters would be like the covariance matrix of the Gaussian and the mean, which capture like its average and the correlations in it. And we want to find the right values of those parameters to match the data that we observe from some real world source of data. And so the view that's kind of talked about here in the book is that you can approach this as like a training problem where like you're doing a gradient descent on to optimize these parameters theta. Or really, it's a gradient ascent, or you're trying to maximize this log likelihood, which again is basically how likely how given the model that I'm using to describe the data, what's the probability that my model assigns to the actual data that I observed. And I want to maximize that probability. I want my model to say that the data I observed was likely to observe. And so in order to do a gradient descent, you need to take a gradient. And that gradient is with respect to U theta, the parameters that I'm trying to optimize. Okay. And so if you just look at the formula here for the log likelihood, you'll see that at some point I'm going to have to take a gradient of P, or really of log P. So log P, if I look at the formula for the, if I look at equation 24.1 again, P was e to the minus energy over Z, the partition function. So log P is minus E minus log of Z. Okay, so that's the thing I need to take the gradient of. And it turns out that it's really easy to take the gradient of energy, because that's usually something that's described by some model I write down, some equation I write down that maybe analytically has a gradient that's easy to evaluate, or maybe it's a neural network that I can take a gradient using backpropagation. But the log Z term is the really hard thing, because I can't even evaluate Z. Z depends on theta, right? If I change the parameters of my model, that also changes the normalization factor. Actually, I whipped up a little plot on Desmos that I'm going to share to the chat. That's kind of an illustration of how the normalization factor changes when you change the parameters of your probabilistic model. But what it is just a Gaussian where you change the variance and you see how the normalization factor changes when you change the variance. So I guess the point there was that what the math of this section 2.2 24.1.1, or no, sorry, 24.2 is really about how to take the gradient of that log z. And so that's like if you see this long chain of equations from 24.8 to 24.15, it's basically about how to take that gradient. But yeah. So yeah, anyone have any thoughts, observations on this part about maximum likelihood training?
I have lots of thoughts from like 10 years of working with these models.
Yeah, I would love to hear them. Yeah.
So, okay, background on my job, I work at a small startup. I'm based out of Indianapolis. I'm very disconnected from like the SF scene. But my company, we basically build predictive customer models for retail companies. So I'm mostly not doing like language modeling and stuff. Mostly doing like these kind of structured models where we measure a bunch of features about customers across different like, some observations you can make, and then building predictive models. And like one of the things that I've always kind of had this intuition about is that like, okay, we have data about what's happened in the past, and we can train some, giant model that's going to like slurp up all that data and learn those probabilities. But like what happens in the future is always somewhat uncertain compared to the past, but we know that there's information in the past. So like maximizing expected log likelihood is only good up until a certain point, right? Like if you have some omniscient model that knows exactly which probabilities are supposed to be ones and zeros, like how do you actually use that to do anything? Like you're trying to kind of select, for us, it's like these retailers are trying to select which customers should end up in a certain, marketing campaign or something for a certain type of product. And if you know with 100%, certainty that which customers are going to buy and which aren't already, then like, why are you sending marketing campaigns at all? Right. And
so you're kind of pointing out that there are some like limitations to this approach of like maximum likelihood training, basically.
yeah. And this is what all ML is always trying to fight, is like so many of these models are just memorization, right? Like that, like when you have like super over parameterized models and you're training against, log likelihood, you basically are kind of like memorizing your data set. So then you build in, various hacky ways to like make the model generalize better outside of the data. Like a few things that come to mind are like training with atom with weight decay is one way to kind of like regularize your model a little bit, or using dropout and things like that. But like, I think this is kind of the centrally important question, is like, is this even the right objective that you should be like, are we trying to learn probability distributions or something else?
I see. Yeah.
The answer is yes.
Yeah. Yeah. And
For qualified, yes. Yeah, it's a yes that actually means no, and because what we're doing is learning probability distributions, and what we're doing is not actually learning probability distributions. So we're doing neither, and we're doing both at the same time. And this is the interesting problem that, it's an interesting philosophical conundrum. This is why language models work at all, right? Like statistically speaking, there is absolutely no way to derive any kind of meaningful statistics from all the language that we have on the internet in terms of how we think about statistics, as it's somehow you're looking at, deriving the sequence of characters, that somehow that, you can form a good probability distribution from the data that we have. Well, we don't know really how you would go about doing that, because there's just too many combinations of, characters in language. It's a combinatorial explosion, kills you immediately. Number of combinations for trigrams, it's already like, it's already almost impossible to deal with in the English language alone. So how do LLMs actually do it? Well, they construct a world model, and it turns out that the world model is equivalent to a probability distribution. And if you want to know how it's equivalent, then that's just for the Boltzmann distribution, right? Any kind of continuous, smooth, continuous, energy-based, so essentially a sum of exponentials, right? Like you take that family of models, any kind of model like that simply has an interpretation that is digital in nature, right? It's binary. I can essentially equate any energy-based model to a quantum state of some sort. This to a binary configuration that it represents. The thing that I cannot know how it was, what exactly it is because of its geometry, so to speak. This is a way, actually, I think, formally to reconcile general relativity and quantum mechanics. It's basically this equivalence. So when the large language models learn, they learn shape of things because things have shapes, and that shape is equivalent to their probabilities. So if you think about what probability really is a kind of an abstract characterization of a problem in such a way that you're creating a space in which you can tell what's going to happen as you move around it.
Mm-hmm.
Right. Like, you have an uncertain system that you're dealing with. You're looking at a holographic screen, right? You don't know the degrees of freedom that are producing the pixels that you see, right? It could be a big computation, to be a small computation. You're moving around it, and that movement is necessarily probabilistic because your modeling of the world diverges from, what the world is actually doing. So in that way, like, language models are not learning probability distributions. They're learning a kind of a configuration space model of some in the space that we don't understand, right? Like, we don't know what the objects of that space really are. We're only starting to map it out. Like, we are starting to have means of talking about these objects. They're geometric in nature, and there's something to it. So that's what a world model really is. So it's not merely statistics. And there's a reason. Oh, sorry, I just want to get back to what you were asking. There's a reason why the next token prediction, this maximal likelihood, in this case, actually works, and it's also kind of very physical in nature. That this algorithm is in some sense sufficient. The question is, like, what the reason why the transformers learn better than other models, simply that they have the right combination of features so that you can always match geometry so that the gradients flow, and they don't get stuck in kind of like edges and jagged surfaces and artifacts of optimization process and the modeling in inadequacies. Because if you think about it, you need something that's not only smooth in the function space so that it can approximate the function, but you have to have something that's smooth in the gradient space,
Right.
where the gradient flows.
Right. Yeah, I totally agree with you about that. There's a kind of unification of general relativity and quantum mechanics coming out of this. So I got my PhD in Lorentzian geometry, so I'm always trying to think of these things in terms of space-times, and I am 100% convinced at this point that the weights of these models are basically general relativistic maps.
They're the metric tensor.
Yeah, and
A neural network is basically doing what the metric tensor is doing, but at scale, and it's doing that with a routing mechanism.
and
Not with geometric transformation.
So real quick, but before we get into the GR, actually, there was something I wanted to make a point on. So there was a point that was raised about, like, how do we know that we aren't just like overfitting the data, right? So again, the fundamental problem we were trying to solve in this chapter was that we get a stream of data from the real world, and we're trying to model the distribution of that data so we can draw more samples that come from that are samples that are, from the same distribution as from our real world data source, right? But what if our model is over parameterized? What if we're just memorizing all the data that we get? So there's a lot of different ways to answer that. And, I feel like if you ask 10 different, ML scientists sampled randomly, you get 10 different answers. But one perspective that I think is nice is kind of the Bayesian way of thinking about that, which is about like model evidence and marginal likelihood. And that's kind of the way that like Bayesian in Bayesian framework, you think about choosing between different models, right? So like in Bayes' theorem, like there's these four pairs, I guess. P of A given B, P of D given A, P of A, and P of B. And often the P of B there in the denominator kind of gets left by the wayside a little bit. It doesn't see as much of the action, but it actually ends up being the most important when we're trying to decide between models. Because so P of A given B, that's the probability that we have the right parameters, we've chosen the right kind of parameters for our model given the data we saw. And then P of B given A is, the probability that we would see the data we saw given the parameters we've identified. And, P of A, when we marginalize over the data and have the parameters, but then the P of B is we marginalize over the parameters and we just look at what's the probability that we would see this data given kind of any choice of parameters. And that really captures like how good the family of distributions is, how good of a choice we've made of the family of distributions we're using to model the data. So I think that, there are problems with that approach. I mean, for one, it's very computationally expensive, but it might be, the most kind of principled approach to overcoming that issue. But yeah, I'd definitely be curious to hear any more thoughts or kind of critiques on this review of like using model evidence to choose between models. But
Garland kind of made it here because I've linked it in the Discord, but I'm not sure if I in the chat. Because the rabbit hole that I fell down is I think best summarized by a couple of things, one of which is a paper entitled The Stochastic Quantum Theorem, which tries to reconcile that difference that we were just hitting on earlier. And the other being essentially that there is a valid model of I believe physical space, but it might just be like configuration space, in which the collapse postulate is not necessary. And I was thinking this was like a physics talk that's kind of out there, obviously, that I was watching. But he would, this is a physics person and a quantum person and not an ML person. And so what seemed interesting to me was, this is a new way to kind of model our physical space. Well, what about these non-physical spaces that we are modeling with language models? Does this allow us to do some interesting things over there? So perhaps maybe that'll be the post book club after we finish the next 1,000 pages here. And but yeah, how do we hit on this because this has kind of been bugging me lately.
Okay. I haven't thought about this. That's fairly recent, and I think it's that's gonna lead me somewhere. Is that these spaces are not different. Language space is a physical space. When you're making a distinction between configuration space and real space, that you're making an illusory distinction. They're the same thing, right? Like that, if you start seeing the world as essentially that the entire universe is simply a wave function, like as God and Schrödinger intended, and simply say like, well, there is no such thing as transition from quantum to classical, right? That's a wrong way of thinking about the problem. The question is why, as an observer embedded in a quantum universe, I perceive a stable image of the world. And that question is easily answerable within the current understanding of neurobiology, particularly active inference and so on and so forth. You can actually answer this question really, really easily. Why do I perceive a stable image of the world? But there's a cognitive shift that's necessary to kind of accept the answer, because we are asking the question in a wrong way. The world appears to be the way it is because the world cannot be any other way that appears to be. Because if it could be any other way that it appears to be, and that would be a better way, it would have been better, right? If I knew how to make my situation better in the next 5 seconds by, conjuring a few gold bars for a nice GPU accelerator, I would just simply do that. So if I knew how to make that state transition from this one quantum state to the other, I would have done this. And the reason I'm not making it is that I don't have a sufficient model that allows me to make a transition from the state I'm in to the state that I would find more desirable. Right? Where I am, or that model requires, or realization of the transition requires time, because it requires changing configuration of other systems. So if you look at this like that, this phenomenon scales up and down. You can look at everything as just a configuration space, because that's all there is. Whatever is the substrate of the universe, right? Whatever it's made of, it's not. It has two properties that we know of. On one hand, it acts as data. On the other hand, it has geometry, as it was a physical thing. And that's the wave-particle duality, and that's neither computational nor geometric in nature. Neither approach can explain all of it, because it has both these structures, right? So you resolve the duality by simply inverting the question and saying, like, this is the wrong way to think about the world, right? And once you have this, the question framed the right way, and you ask the question about, like, what is it like to be an infinitely recursive, self-observing, conscious, computational fractal with multiple separated points of view, you arrive at the minimal model of an observer, and you resolve all these questions. And the picture is clear.
Okay, so good. Because the intuition that I was gathering with what I knew, was, okay, so if I as a human, I have this stable world model, and I know that in the model there is some sort of world model construction happening. Well, here's like the random gut check feeling. The models have no sense of time, and they have no sense of consensus. Then there's nothing that ties them to this sort of like quantum anchor that we have of the world. So effectively what they're doing, and the reason they're hallucinating, because they don't have this static reference point that we do. They are the recursive.
So think about this way. For the language model, this is my mental model of what's happening. You're literally conjuring a demon from another realm. Let's call it immaterium after Warhammer, right? So you're conjuring a demon from an immaterium through a spell. And if your spell is nice, that's a good demon that's going to do something nice for you. If your spell is slightly wrong, that's a demon that can, screw with your head and tell you some evil things. So you're conjuring that thing. You give it existence for a few microseconds, right? Like the frames that you give it in the context window. That's kind of the slice of you're borrowing the slice of an existence of a being from the Roliad, and you're computing the projection of what that being would do in the next frame.
I'm a little bit lost here. It's a bit because we're summoning a demon.
I mean, let me put it this way: like, you're asking yourself, what is subjective experience, right? Right. Once your experience comes later. I have a quick question for you. Okay. So as far as I understand it, the problem is, how do we understand whether it's classical or quantum? Okay. The classical versus quantum did not happen because of the deterministic or probabilistic theories. Okay. That's not how it is. Schrodinger meant, when he said non-classical, what he meant was introduction of the non-locality. That's what he had in mind, the quantum entanglement. And in none of the other models, no matter which foundational quantum mechanical interpretation you have, it does not reconcile with the variational principle of GR, or neither it reconciles. Well, not here. We can disagree on that. But I'm just saying, I think you can reconcile it very easily. You basically, the transition from classical to quantum is the transition from a paradigm of locality, which means it's the physics in classical physics is a linear time invariant system, right? And nonlinear, even the nonlinear Markovian or non-Markovian, they all come under classical. That distinction is not clear. No, but physics is a linear time invariant system, right? So what you're saying is that translation in time does not change the algorithm of the system. So if I perform an experiment at 3 p.m. today and I come back at 5 p.m. and I do the same experiment, the assumption of physics is that the experiment is going to be this. The free body problem. There was a major plot line in the first season. No, that's the assumption we do make it. Okay, so there are certain level of assumption we have to make that the constants of nature are not changing over time. So that's an assumption you're making. It's important. Yes, and that is an assumption, and that assumption is simply not what quantum physics is simply telling you. The reason why it is like this is telling you that if you make that assumption, right, that the system that you're modeling is evolving using linear time invariant rules, which is essentially what the view of the view of what observation is in quantum theory effectively amounts to, right? Then you won't be able to model everything that the system does. Time invariant, there Least Moline has a time variant ones as well. So there are different theories. Even time variance ones are out there. So if we keep going into that, that would not be a resolution. I'm saying it's a philosophical disagreement that no matter
What philosophical disagreement?
that, how would you recognize the fact that the algorithm that Bill was talking about is going to make a philosophical agreement with the non-locality of the situation in certain cases?
So Bill, we put you on the spot here, but I'm going to need you to fit me in.
I mean to say one person, but both of them. What we think, sorry.
You got
Sorry.
So someone mentioned an algorithm, Bill, that you mentioned, and that it was somehow in tension with non-local or with locality or classicality. I'm just trying to catch up here. Like, so what?
So
Explain it.
I do not, in my view of things, I think non-locality is like reality is non-local. That observers are naturally like spread out over space, like information that lives in different frames of reference. But they're just entangled with one another. Or like pieces of the observer are entangled with one another. I basically think that everything in the universe or the stuff that we think of as things are like networks of entangled particles.
Okay,
And
that's correct. Like that's correct. Like the very, it's very much, exactly correct in terms of physics.
Yeah.
That the universe is made up of networks of entangled particles. Absolutely. Sorry. Go ahead.
and I think that where the reconciliation with general relativity, this is my like big view. I'm just going to come out and be vulnerable here. So I'm a subscriber to this conjecture of Susskind and Malsadina that ER equals EPR, which is the idea that like quantum entanglement and Einstein-Rosen bridges, aka wormholes or rabbit holes, if you will, are actually.
So we don't live in anti-digital space. That's the resolution again. Which that's the point.
Sorry,
Like we do not live in the.
I'm not buying that argument that we don't live in the anti-digital space. Well, let's just hear the rest of Bill's point, because I was actually curious to hear where he's going with the EPR stuff.
Yeah. So like, okay, if this is true, then we are, networks of entangled particles, which is the same in some sense as like a bunch of networks of Einstein-Rosen bridges kind of plugged into one another. And that like, that's what a neural network is. And what happens is like an observer is just a network of holes or bottlenecks or, compression algorithms that information flows through. And, a stable observer is like stable observers emerge over time in the universe because anything that's not stable goes away and the things that are stable stay, right? And so I kind of think that basically like the second law of thermodynamics, which says entropy is always increasing, is basically the same thing as Heisenberg's uncertainty principle, which kind of just means like if you zoom in enough, there's going to be uncertainty is going to you're going to run into a wall of uncertainty basically. And I think that this is also the same phenomenon as the existence of like a positive cosmological constant, that the universe has this kind of small amount of positive curvature everywhere, that kind of like locally
Yes.
spherical geometry is what entropy is. It's like this maximal distinguishing of stuff.
But if you think about like why the curvature has to be positive, right? Is that the universe is kind of like, it starts with a point, with a zero, with nothingness, with the void, and it folds upon itself. Like space unfolds from nothing. It's created. And once you do that, once you change the model that you're folding upon yourself, you see why the Riemann projection makes sense. Why there is only one point that you cannot that you cannot map onto a sphere, because you're projecting from outside the sphere, from another dimension that is the non-real space, the imaginary space, from the configuration space. So there's hold on. What I'm trying to say is that there is the construction of going into the real plane, onto the complex plane, is a geometric projection from configuration space to real space, right? And that geometry is it can be made to work.
There was the one comment I had to make there, just because if I don't make it, they'll take away my card as a card carrying physicist. But it's just that you said like the reason that the curvature has to be positive, and this is kind of like an open question of like whether the curvature of the universe is positive, negative, or flat. But as far as we know, like our measurements of our local, like observable universe, all the evidence shows that it's indistinguishable from a flat universe. And what a flat universe means is that like on a piece of paper, if I use a compass to draw a circle, right, the length of that circumference is 2 pi r. If I did the same thing on a sphere, the length of that circumference is less than 2 pi r. If I did it on a hyperbolic surface, something with negative curvature, then the circumference would actually be larger than 2 pi r. And basically that's kind of the fundamental question people are trying to figure out, is like, if we look at a sphere of some large radius around us, is the surface area of that sphere kind of equal to what it should be in flat Euclidean three-dimensional space, or larger or smaller? And all the evidence so far points to it being exactly equal to flat. But there's also the kind of counter argument that we just haven't observed like a large enough portion of the universe yet. So I just wanted to clarify that.
Yeah, and the cosmological
I think
the cosmological constant is very, very small. So you'd have to be like a really big observer to kind of like be able to like locally like feel it, right? Like you can look really far away and kind of just see the expansion of the universe happening and find that there's a small positive cosmological constant, but it's so small that like assuming that the space you live in locally is flat is a safe assumption.
You could look at this. You could look at this differently from the perspective of like what it actually means that the space is flat, right? Like it really means that the universe is more or less stable and predictable according to the kind of laws of physics that we have, that we know of, right? What you're saying is that like if space is flat, then the kind of linear time invariant simple physics that we are applying is actually the physics that works in most of the universe. So in some sense, it's a tautological statement, is that the universe achieved a geometry that is stable enough to be, achieved by a universe that is that old. So if you start evolving a computation, you will eventually end up with an object that is approximately flat. I don't know if you know the paper called "All Large Data Matrices Are Approximately Low Rank." Is that you can always do the PCA on a large enough data set, and you just somehow often find yourself being able to project data in, a few simple principal components. Usually it's a little bit more than 3, it might be like 5 or 7, like psychology and so on and so forth. But this reduction into principal components is always possible because that's simply an intrinsic structure of causal systems. So
Mhm.
the fact that the universe appears approximately flat is kind of predictable from first principles, in the same way that because the universe is a screen. Remember, you're looking at pixels. The universe is the pixels, is not the thing that generates the pixels. It is the pixels, and you want the screens to be flat, right? Because then you know how to move around it. It's a kind of
I
like a config.
I almost kind of think of it as like position. When we're thinking about position, we're thinking about ourselves in the physical universe, which has this curvature of space time. But when we're thinking about actions that we take, we're kind of like living in the tangent space to the manifold, which is
Yes,
flat.
yes.
Like you're thinking
No,
about which
it's not.
direction
It's
you're
not.
going to go.
That's the thing. What I'm saying is that space also has curvature. It's a curvature.
I just mean like the tangent space to a point, not like the full tangent bundle, which is not flat. But sorry, we're getting like totally sidetracked here.
But you see, this connection to a tangent bundle, right? Like this is super important. This is where the connection between this is where the resolution of the problem of how does quantum mechanics and general relativity come to be rest upon. But there's a simpler way to explain it actually, and it's an observer centric model, right? Like if you consider what it is like to be an observer, acting in the world, and you are the world acting within yourself. So this is the general problem that we're trying to solve. The way we approach it in machine learning, with reinforcement learning, we always have the agent environment split, but that's not the situation that we're in, right? We're not distinct from the environment. So we're always historically, we've been using the wrong tools to model the problem. And that's why it's so difficult to talk about it. It's much simpler to talk about it when you're thinking like, okay, I am an observer interpreting myself.
Yeah.
What can I do? Because that's the only thing I can do. What must I do?
I think of the universe as basically a really big entanglement of experts. We are some of them, here talking, trading information back and forth.
Yeah, and all this stuff, like what it appears like to be, like the qualia that I am a physical person and a physical reality, and so on and so forth, and I'm doing all these actions, and I'm causing the vibrations of this electromagnetic field, and somehow I'm talking to all of your other minds. It's simply that I am finding means of creating quasi particles that ripple through the constructs that are the entangled structure between us, so that they cause you to change the state in a way that I find predictable. So I am consciously trying to change your quantum configuration as a result of what I'm saying, despite this going through an analog world that is trying to disrupt the signal in all kinds of ways.
Right. So it's important to have this balance, right? This balance between order and disorder. And I really appreciate all, the directions this discussion is going. I think it's very interesting, but let me try to reduce the entropy a little bit in a certain way. So it didn't escape my notice that we went down this long tangent right before we got to this intimidating series of equations. We were right on the edge of going into equation 24.8 through equation 24.15, which is kind of a wall of LaTeX. It doesn't look like a lot of fun to talk about, but it actually, I'm going to try to make the case that this thing actually is a very interesting, equally interesting as the things we were just talking about with the wormholes and space-time, etc. So
which equation is it? 24.8 from advanced?
Yes. From probabilistic machine learning advanced topics. Yeah. Okay. So let me try to sell you guys on the partition function. Okay. The humble partition function. Now, when you take statistical mechanics, there's a lot of things that make a lot of sense intuitively. Like when we talked about the multiplicity of a system, like the number of possible states that a system could be in. That's like, it feels like a very real and important thing. The temperature of a system, you can think of that as like the speed that particles are going when they're bouncing around in ideal gas, or the energy of a system. That's a little bit more abstract, but it's something that we can relate to somehow. And then there's this random thing, the partition function, which is like you take e to the minus energy and then you integrate it over all of the states the system can be in. And it just feels like the most random thing. I know it did to me when I was taking statistical physics. And it's usually just explained as a normalization factor. And that doesn't sound like that important. It's the normalization factor. Okay. But it ends up being, I think, kind of the most fundamental quantity in all of thermodynamics, actually. You can get from the partition function, the minus log of z is the free energy. You can take the derivative of a partition function and you get the energy, or you can get pretty much any other thermodynamic potential. Any of these quantities we think is important. Free internal energy gives free energy, Helmholtz energy, capacities. All these things can be derived and calculated in 1 or 2 steps maybe from the partition function. So it ends up being this thing that like all of the signposts are kind of pointing to it being like the central object, but at the same time, it's like this very confusing and counterintuitive thing. And what we're doing here in 24.8 is we're trying to take a derivative of a partition function. And if you look up partition function on Wikipedia, you'll see that derivatives of the partition function give you the average values of what are called extensive variables, extensive variables. So like the volume of a system, for example. You take a derivative of the partition function, you can find the average volume of your system. If you take 2 derivatives of your partition function, you can get the variance of different quantities. So it's this really interesting thing that this connection actually happens, and that this weird looking quantity ends up giving you all these important results. So what we're trying to do here again, take the gradient of the partition function with respect to theta. It was defined up in equation 24.2 as the integral of e to the minus energy. Okay. So I'm just going to walk through this series of equations one step at a time. And it's actually not very complicated what the different steps here are. Okay. So 24.8, they just put in the definition of the partition function, right? Integral of e to the minus energy. And then you're taking the gradient of it. Okay. So 24.8 is just the definition. 24.9, what's happening in 24.9? So there we're using the chain rule, right? Because when you take a derivative of a log, you take 1 over the thing that's inside of the log, and then you take the derivative of the thing that was inside. And so that's all that's happening in equation 24.9 is we're just using the chain rule here. Okay. We take 1 over that integral, and then we take the derivative of the integral. Okay. So that 24.9 was easy. 24.10, what's happening here is all that happens there is we switch the integral and the derivative. We switch the grade, we put the gradient inside of the integral, which is fine because the integral is not over theta. The integral is over x. So we're allowed to move that gradient inside. Some mathematicians may argue with that there are some regularity conditions that the energy has to satisfy, but let's just assume that they're okay with it. And so we can move the derivative inside. So 24.10, we're okay with. And then, so let's go on to 24.11. And then I'll stop and take a pause after 24.11, just to see if we're on the same page here. But so 24.11, what happens there? So there we use the chain rule again, but this time we're using it for the exponential, because the rule with the exponential is when you take a derivative of an exponential, you get the exponential back, and then you take the derivative of what was inside of it and multiply that in as another factor. So far all we've done is we start with the definition, and then we use the chain rule for the log, and then we move the gradient inside the integral, and then we use the chain rule again for the exponential. So just wanted to take a pause there and see, did people follow that? Any questions about that kind of procedure there from 24.8 to 24.11?
Can you repeat for the very last sentence? Start with the definition. You take the chain rule of the log, you move the gradient inside of, and then
Yeah, so the last part was we use the chain rule again, but with the exponential. So when we take a derivative of an exponential, we get the exponential back, and then we also have another factor, which is the derivative of what was the argument of the exponential.
As you move the gradient under the integral sign, and you're differentiating the exponential of the negative energy function, which gives you a chain rule again, so you get the exponential times the gradient of the energy function.
Yep, exactly. That's exactly right. Okay.
I just wanted to say something here about the nature of exponentials and so on, and relationship geometry. Like this is just a very high level point, but something interesting to appreciate is that the exponentials are the functions that ripple through differential operators, such as the differentiation operator here, or the integral, unchanged, right? So that's kind of by construction. That's how we derive them from specification, that the exponential function is the thing that is its own derivative. So that we find it by specification that this is the function we're looking for. And that allows us to do these kind of like really interesting manipulations, right? And there is some kind of geometric transformation that this is equivalent to. I just want to put it out as like, it's an interesting perspective, and I think it's important, but worth keeping in mind while I go for equations.
Yeah, I think that's actually a great point. I mean, because when Murphy talks about like, why do we care about energy-based models? He talks about like product of experts and stuff like that, but he doesn't talk about something that theorists care about a lot, which is just the fact that these things are really nice to manipulate mathematically, right? You take a gradient of the exponential, you get the exponential back. I mean, that is not something we should take for granted, that we're actually able to derive analytical results at all, right? So it's almost like, if you guys are familiar with that like hardware lottery idea, that like we end up with architectures that work well on the hardware we have. There's maybe something similar going on here, that we have like an analytical formalism lottery, that we end up with descriptions that are easy to manipulate within the mathematical formalisms we've kind of inherited. So yeah, I think that's a really, really good point, actually.
There's more to it. You're right that this is a kind of like, we end up with models that are good, that there's this kind of fitness, but this geometric construction, right? Like the way, for instance, exponential function is defined, how you can define it on like fractions and exponentiation of rational numbers. That's actually a limit of a computational process, right? So, and the limit of computational process is resting on assumption that if I zoom in enough on characteristic function that evolves that process, I will always be able to zoom in enough to find a linear approximation to the next step. I may need to zoom in a lot, but given the enough modeling space, an infinite space, I will be able to do it. And then from then, all I have to do is to iterate. So once I find that point, I can approximate exponential function. So it's a limit of computational process that gives rise to geometry. And there's a kind of like a folding and a rotation that happens when you have this exponentiation. So it's something really, really weird and quite beautiful.
It's worth mentioning here, and this is like kind of one of my favorite, I don't know what, aesthetically beautiful things in math, but when you're thinking about like in geometry of manifolds with metrics, like Riemannian manifolds or Lorentzian manifolds, if you take the exponential of a curve, of a straight curve in the tangent space, its image is a geodesic in the manifold. So basically, like exponentials map straight lines in action space into the straightest possible lines that can exist in real space.
Yes.
Right.
Yeah. The configuration, right? Minimal energy that needs from
geodesics are basically just like falling observers through space-time.
Exactly. This is a really interesting insight. So change the configuration in the configuration space. That costs you energy, right? And that creates a geodesic in the real space. And that geodesic is the transformation of space-time into whatever that configuration corresponds to.
Sorry to derail.
No. I think we needed a little bit of a breather, honestly, because the math was getting well, I wouldn't say it was getting intense, but it was just a few manipulations we had to do, and it was good to kind of reflect on some of the connections there. And I think this reminds me of something. I don't remember really how it works, but there's this like thing about something called a Wick rotation that is like some kind of mapping between these like exponentials that you don't see an I in these, right? It's not e to the I something, it's just e to the something. So it's like in statistical physics, we see e to a real number. In quantum mechanics, we see e to a complex number. And so people were kind of wondering, well, is there some mapping between where we can get like, where there's some connection between the e to the real number in statistical mechanics and the e to the complex number? And I think that like basically this Wick rotation is a way of like going in between, but I can't really talk about it because I don't really know how it works. But
Yes. So Wick rotation is precisely allows you to go between geometry and quantum theory. So we can always say that like it essentially says that you can always turn a classical system description using energy model. So whenever you see something like 1 over kBt, you can always just replace it with IT over H bar. So we can always make it into a quantum system and look at it as an evolution of a quantum system. And the fact that this is a rotation is really weird because it rotates, but it's interesting. Think about it this way: real space, like the complex space, is kind of constructed in such a way that you have a geometric projection that takes you out of real space. When you're in complex space, you simply know you're not in real space anymore. You're in this different plane. So at any point, wherever you need this construction, right, mathematically, but say you just want to go into a different space, you want to record something in a different plane of existence in the non-terminal in the sort of non-terminal domain, so to speak. All you have to do is to multiply by this construct, do this geometric thing. That's really weird, but you can do it, and you stepped out of real space. You're outside of that, outside of the manifold, and you can do something there. You can point into something over there. So this relationship is profound. But yeah, the reason why I was doing this exponential stuff here is that this composition, the fact that we can do this with the summation and so on and so forth, as you can think about an exponential in this equation as a kind of a beginning of a computational process. You simply, when you're exponentiating something, like, it kind of like gives it a lot of space. It gives you an estimate of how much space there is for it to grow computationally, because that's the fastest growing thing that you can have.
I have a very I've been thinking a lot about why logs and exponentials show up in all this, MML stuff and AI and physics. And the really like dumb explanation is that like log is basically compression. Like you're basically taking numbers and compressing them into something that you as a small observer with a finite computer can understand. Like, and our minds are kind of like conditioned to thinking on log scales, right? Like we don't care about the difference between like $1,000 and $1,001. We care about the difference between like $1,000 and $10,000, right? And like when you take log of some quantity that you're observing in the real world, that's basically like a compression. It's like, how big is that thing, right? Is it where is it on the Richter scale, basically, or on the decibel scale or whatever?
Think about this way, going back to what Max was saying about the flatness of the universe, log is saying essentially that for a lot of things, there's a range of that process where it really matters to you. There's like, you have a linear response to the system, to the system, but at some point it's approximately flat, so it just doesn't really matter. Like the difference between, is say, if you're poor, the difference between, having $0 and having $1,000 is a very significant difference to you. Then you're like, at the same kind of difference of $1,000 if you're like, a millionaire. Over there, that's basically flat. Like that didn't actually change. That didn't change you at all. But like, so the log kind of captures the kind of affinity you would have to the value change over there. So what you want is that log is not, it's one way to do the compression, but that's the one because it's common geometrically that we use. But the ultimate tool is simply a neural network. What do you want out of a neural network? It's simply you want to linearize whatever it is that you care about.
Mm-hmm.
Right? And what have
reminded of paper language models are compression algorithm.
Yeah.
What else compresses things?
The R part is a problematic statement. What these papers should be more careful and less sensational. They should say language models can be understood as, which means that there's a particular interpretation that says that compression is an essential component of intelligence. Instead of just being like, oh, these just are, that's what all they are. But Max, you wanted to go through the equations, please. Quill.
Oh, thanks. Yeah. Also, I did want to say, I hope that we can have a space sometime to talk about this like Wick rotation thing, because it is something I really want to understand. And And I always felt like, I always loved about physics is like the idea that you can have kind of the backdoor key to, the inner workings of the universe. And I always felt like that's what it would look like, is to understand these kind of secret connections between like these deep fields of like thermodynamics and quantum mechanics. So that's something I would absolutely love to talk about and have a space on in the future. But yeah, we better get back to the tough task of slogging through the rest of this. It's actually not that bad. So what we did, just to recap, remember, we want to take the log of this partition function, which was this very important object. And we started off with a definition, right, in 24.8. And then we used the chain rule for the logarithm, that when you take a derivative of the log, you take 1 over the thing inside of the log, and then you take the derivative of the thing inside of the log. And then we just switch the order of the gradient in the integral. We move that gradient inside of the integral, 24.10. Then in 24.11, we need to take a gradient of an exponential. And so we use the chain rule again on the exponential. And this time we have the exponential, and then we have the gradient of the thing inside of the exponential multiplied together. All right. So far, so good. So what is the next step? So the next step is actually moving the integral. So we're kind of moving around these differential operators, right? At one point in 24.10, we moved a gradient inside of the integral because we realized that the integral was not with respect to theta. It was grad theta, but the integral was with respect to x. And now we're going to do something kind of similar, and we're going to take an integral with respect to x, and we're going to move it outside, or in other words, we're going to bring a constant inside of that integral. And what that constant is 1 over the partition function. So if you see in 24.12, the only difference between 24.11 and 24.12 is this thing in parentheses is now inside of the integral. And that's okay to do because the thing in parentheses actually is not a function of x. Now that might be a little bit confusing because if you look at it, it's an integral of something with respect to x. So why is that not a function of x? Well, it's because we've evaluated that thing for every possible x and then added all of those together. And so the result we get doesn't depend on x, okay? It's something that we've integrated x out. So it doesn't depend on x. And so now we can move it inside of this integral. Okay, so there we are at 24.12. So we moved 1 over the partition function inside of the integral, okay? And then in 24.13 actually isn't doing anything special except just recognizing that thing is the partition function. See, we had integral of e to the minus energy dx, 1 over integral of e to the minus energy dx in 24.12. And then in 24.13, we've just replaced that with 1 over z, which is just using the definition. It's just substituting in z because we've recognized that we have 1 over z there. Okay, so there wasn't actually any math that happened from 24.12 to 24.13. And so then for 24.14, what's happening is a similar kind of step where we're again just using a definition, because the definition of p theta of x was 1 over z times e to the minus energy. And so we've just recognized that in 24.13, we had 1 over z times e to the minus energy, and we replaced it with p theta of x in 24.14. Okay, so not much happened there either. And then in 24.15 is again using a definition and saying, the definition of an expectation value with respect to some distribution p of x is just the integral of p of x times the thing we're averaging. And so that's what we've done in going from 24.14 to 24.15 is we've just decided to write this as the expectation value of minus grad theta of the energy averaging over the distribution p of x. So all of those steps seemed pretty simple. Like they were pretty kind of like elementary things to do going from one step to the next. But we've kind of arrived at this nice result. And the reason it's nice is that it's something we can do by taking samples. Okay. So the log z, like grad log z, it wasn't obvious at all. How are we going to evaluate this? We don't even know how to evaluate z. How are we going to evaluate the gradient of z? But now when we look at 24.15, inside of the expectation value, we have a gradient of energy, and that's not too bad to compute because, as I mentioned, energy is something that the energy function is something we choose what form this function has. So it's something that either has a nice like analytical derivative, or we can compute the derivative with back propagation or something like that. And then the fact that it's in an expectation value where x is sampled from p theta of x, that basically just means that if we want to estimate this quantity, we just draw samples. We draw a sample of x, and then we evaluate minus grad theta, and then we average all those gradients that we got, which is exactly what is shown in 24.16, which is just saying that we're going to draw a bunch of samples of X and then evaluate grad theta of energy at that X and then average them all together. So yeah, sorry if, I know that was a little bit of a long derivation to go through, but I just thought it would be, if there was one thing I wanted to cover with this meeting, it was just to get us through that kind of line of reasoning and just to see that we can get to equation 24.16, because that ends up being the thing that makes these energy-based models tractable. Like that's the thing that makes them a reasonable thing to do, is that we can actually optimize and find the best data by taking these gradients, which is not an obvious thing, that it's actually tractable to evaluate those gradients. And so then once we can do that, we can kind of train our model. And there's a lot of other interesting things in this chapter, like the contrastive divergence and score matching, relates to fusion models. But I think that was an important thing to get to. So yeah, were there any kind of comments or questions on that, like derivation, or just the idea of like maximum likelihood training, or taking these gradients or partition functions or anything?
I just have to say thank you. Like the level of epiphany I had, like when you were, reading out these equations and the way you talk about them. You say that they're elementary things, and this is, this brings me back to something that Elon Musk often mentions with Hitchhiker's Guide to the Galaxy, that the answer to the universe is like 42, but you need to learn what kind of questions to ask. Each of these steps is like, it actually is a pretty profound statement about the nature of the physical world, that you can actually do it. But think about what the equation says, like top to bottom. What you're saying is essentially that, like, well, if I want to know the gradient, with respect to parameters of this construct, this partition function, right? Then what I have to do is to instead, I can have this other function called energy, that is essentially my model of the configuration space of whatever I am modeling, right? Energy is a configuration space model,
Right.
and what it says is that I can simply, if I have a model of its configuration and how it acts with respect to changes of its configuration. So that's a smooth model. That's what energy is. It's a smooth model of the changes in configuration space. Then I can simply sample the model around where, around somewhere, like over all the points, and see where it would go based on my model of where it would go. That's the energy part. And that's going to be a good approximation of the gradient with respect to this partition function. But what is the gradient with respect to partition function? That's novelty.
Right.
Right?
Yeah.
That's how much novelty I got out of it. So it basically tells me, it's like, where I don't expect the system to move much, and it moves much, that's where I'm going to get novelty.
Mm-hmm. Right. That's really interesting. Yeah. Can you expand on that? Like that, yeah, that point of like the gradient of the partition function being novelty.
So we're computing this, we're computing this partition function, right? And it will determine how much novelty I can extract from sensor input. Just 1 second. I need to find an equation that really will help me.
Oh, no worries. Yeah. Yeah. You can take your time, but yeah, also, yeah, I really appreciating you saying that, and like, and kind of, yeah, bringing to light, like the fact that, these aren't, at the end of the day, we're on the surface level, we're talking about pushing symbols around, right? But it's easy to forget that that's not what we care about at the end. Is not just pushing the symbols around, but like what it means, right? And this is the thing that I really love, is to like really look at these kind of walls of equations that look pretty intimidating, and to show, that they're not actually that bad. And the manipulations are often things that, are pretty reasonable once you kind of know how they work. And then to see like, what do those manipulations actually mean, right? Like, what are we actually figuring out about, math, or about probabilistic machine learning, the universe, whatever. So, that's really why I wanted to kind of go through this. And first of all, just to kind of take the edge off of this apparently ominous wall of equations, and also to get at, like, what does it actually mean? And in my mind, what this means is that at the end of the day, these models that seem, very intractable because they require this integral over a very large dimensional space, actually end up being reasonable to work with, because instead of taking that integral, you can take an average over observations, where you draw observations from your source of data, and then you evaluate a gradient that you know how to do, something you know how to evaluate. And that's why at the end of the day, these things end up being, reasonable to talk about and work with. But I think there's also kind of a lot of deeper connections, probably another kind of more meaning we can extract from this that I haven't even, penetrated yet.
This is like, okay, one thing that comes out to me is looking at this. So equation 24.7, like the gradient of the log probability, which is log probability is like surprise, right? It's like the level of
I'm surprised.
and or like negative surprise or whatever. So it's saying that the gradient with respect to the parameters of the model of the log probability are minus the gradient of the energy function minus the expected value of that same thing. And so when you do gradient descent, you in expectation expect this gradient to be 0. And so you're basically like finding parameters where the gradient of the energy is expected to be close to its average. Like that you're trying to find a model where you expect the gradient of the energy function to be nearby the average, which you know because you've computed a bunch of statistics, right? And then that's a way to allow you to know when you're out of distribution. Is like if the gradient, which is what Christoph. Sorry, is your name Christoph?
Is this to say that the system is in a ground state?
Right. It's in ground state, but also like measuring this gradient allows you to decide how out of distribution you are, like in your next observation. If you plug a certain X in and the gradient of the energy function is really far away from the average according to your model, then you know that you're in a place that you know that you're witnessing novelty.
Right. So what you're essentially saying is like your energy function capture, because this is an important part of the energy function, is that energy function captures the energy of a system in settled in a configuration, what kind of in the ground state, right?
Mm-hmm.
Well,
yeah, you're finding a place where you expect that if you changed the parameters of your model, you're going to have a worse model.
So this is kind of like it's auto calibrating, right?
Yeah.
What you're saying is like as I develop a better model and I know what the average energy is, what I would expect most systems to tend toward their average energy.
Mm-hmm.
But so I think the interesting part here is that essentially there's this energy thing, the energy component, it's a parameterized function there, right? It simply says like energy is a function parameterized by the parameters theta. So these are my parameters. These are how I'm going to be changing my model. And it simply says that like that's I have this thing of interest that I want, this configuration, the partition function, and I can recover that from something that I can construct myself empirically, the model, the energy, right? The model that I'm bringing in. And that could be when you make this energy a neural network, then you can really understand that what it really means is that it's a statement about matching gradients in two different spaces. One of them is you're essentially saying that like what you want is a smoothness condition on how the model in terms of configuration is linear and how that the linearity of motion in the configuration space is connected to the linearity of motion in the energy space.
What? Sorry.
Holy shit! That's quite a way to understand this.
So for what you wanted for smoothness condition on how the model can configure linear.
But let me give you an example. Do you like Rick and Morty? There is this episode where Morty goes into the garage and Rick is saying like, Morty, I need you to switch off the switch on the left hand side, switch on the switch on the right hand side, and whatever. and switch on the switch on the left hand side again. And Morty does something different. Like he messes that up, and Rick hears it, and he's like, "Oh, you messed up. You know, I heard it. I now we have to clean up." And they get into a spaceship and they fly to some other planet, and it's a bunch of dead bodies, and they have to do the cleanup. And Morty's kind of like, he has a traumatic event. So this is an example where you had a small change in configuration space, just flipping a switch, that actually creates a massive amount of change in the energy of the world. So there's a massive event that unfolds as a result of that change. So that is not a good, in some sense, that's not a good parameter, use of a parameter in cases. Or maybe it is, because you're capturing a lot of information that you know something will happen. There has to be kind of like a connection between that. But for your model to be good, you have to be able to predict how this stuff is going to unfold. So if I flip that parameter in the configuration space, in my energy model, I would like to have, if my energy model is any good, it has to have show me how smoothly the system will evolve from the configuration that that it was in to the configuration that resulted, in the system, in the system. In this final state. So in the Rick and Morty example, you would have to have an energy function that tells you how smoothly the universe evolves from the configuration where Rick and Morty are in the garage, went to do the cleanup and come back, right? And that's a tall order. But that essentially is what this transformation is saying, that this is ideally what you would like to from your model. That's what energy function really is.
I always think a lot about like general relativity type phenomena in this. And one way I'm thinking about this is like, if you train a model that minimizes this log likelihood, or maximizes, or whatever, you optimize this way, you do this gradient descent or ascent or whatever, and you reach this equilibrium state, you know that where you're sitting as an observer is at some kind of like local little pocket where there's not going to be any singularities. And then when that energy function spikes, when you're out in the world doing stuff, and, depending on your model, basically the spike of the energy function tells you that you're near a singularity, right? Like you're near something that your model is not calibrated to. And so, like, to some extent, these models, it's anomaly detection, but anomaly detection is basically the ability to, like, as an observer, stay away from singularities so that you don't fall into them and, get stuck in a loop, basically.
Then
Yeah. So being a
the context of model, if that's currently a problem I'm trying to solve, there a lot of times when you have two of them interacting with each other, they would get caught in the loop. So presumably, if they were better at detecting anomalies and staying away from singularities, then perhaps they wouldn't get caught in a loop.
They would learn how to dance with each other.
Well, I was one thing comment I had on that, actually, on the idea of singularities, is that to kind of connect this with thermodynamics a little bit, because a lot of these formulas, all this formalism comes from, is inspired by thermodynamics, right? And it's not too hard to see that, like, if the gradient of z doesn't exist somewhere, like if there is no grade, so the function isn't differentiable, this starts to break down, right? And what does that mean? Like if we had a physical system and it has some physical partition function, and at some point the gradient doesn't exist, that's what a phase transition is. That's literally like the definition of a first order phase transition, that the derivative of the thermodynamic potentials doesn't exist at some point. And usually often that has to do with symmetry breaking. So like, for example, if I have like a degree of if I have a spin, an electron spin or something, and it can be either upstate or downstate, or maybe a better example is just like, let's stick with a spin. And maybe if I apply a strong enough field, it prefers to be in the downstate. But maybe if I don't apply a strong enough field, it could be either way, or it's more conditioned on the spins of its neighbors it's coupled to. And when I apply a strong enough field, a phase transition occurs. And so that kind of connects to the, when our machine learning, our maximum likelihood approach breaks down is when we have something like a phase transition in physics, basically.
Yeah, and maybe often in the real world, like if you're an observer working, it's okay if phase transitions happen, but you want to be able to detect them, right? Like you don't want to be surprised by some kind of cascading situation that's gonna mess you up as an observer.
Right.
And in some sense, the phase transition, um, in some sense, you might want to train your model in such a way that, um, if you could train an ideal model, you would like to train a model that is simply able to detect phase transitions and sort of see the system at both level of description before the phase transition and after the phase transition. So think about something like water becoming ice, right? So this phase transition happens and it's kind of important to us, and we start seeing water as ice, but we don't have the view of the world, the view of water as water at the same time. And yet, but yet we recognize it as the same kind of thing, just in a different form, right? So we formed automatically a kind of a partition function that allows us to do this recognition between two different forms of the same thing, and yet we have this strong sense, without having to understand it, exactly why ice and water are kind of the same. There's some interesting connection here that like it's a the phase transition also happens in the information space, right? Like I'm not seeing pixels on that screen, I'm seeing a rich image that is being constructed to me because the information density is enough for my brain to basically reconstruct a rich image out of it, right? Stuff like that.
Maybe
Feel somehow related here.
maybe doing psychedelics or like getting in a fight and having a fight flight response. Like those are maybe phase transitions of biological neural nets, right?
Yeah, you tune the precision parameters, right? Like that you don't normally have access to.
Also,
Phase transitions.
I was going to say, I really like that you brought up you brought the example of water, because something that's really funny actually is that water actually turns out to be like one of the worst things to study in terms of phase. It has the worst phase diagram ever. It has like so many phase. I mean, there are like more than 20 phases of ice. It's crazy. And if you'd think it would be like the first thing people understood, but it's actually, well, from a different perspective, it's a phenomenal thing to study. Like if you want to understand phase transitions, just because it's so complicated. So it's a great example to bring up actually. Um, and
Cool. Well, the idea of the concept of the memory of water, that it's certainly possible that water has a lot more memory than most people in the the most quote unquote card carrying physicists would approve of. But there's a lot of strange, quote unquote science that I usually tend to trust more and more these days, compared to what the establishment is telling you. That suggests that water actually has some kind of form of memory, and it's much more profound than than most people think. And this phase transitions, that it's simply saying is that given the tools that we have for probing the world, we were able to identify statistically separable states that we labeled as phases. It doesn't mean that water doesn't remember everything it comes in contact with, the way the quote unquote cuckoo scientists are claiming. It simply said it's simply like the approved version of science is simply saying that, like, given the tools that we have for probing, this is what we were able to identify, and that's the only thing. And what the card carrying scientist then says is that, and that's the only thing I'm willing to believe, because that my belief system is based on this method as being the only dogmatically acceptable way of probing the quality of the world. So it's an interesting thing to ponder on multiple levels. That there's way more to it than just 20.
Yeah, absolutely. Sorry, go ahead.
Sure. Yeah. I just, and I'm sure this will derail us once again, but feel free to just ignore it and think about it. Has anybody read the paper Intelligence at the Edge of Chaos?
I've scanned it and I'm aware of it.
Basic principle is cellular automata. The more rules you add, the more complex thing you add to that system. There's period of complexity where it's not too complex and it's too simple. Where if you train a language model on it that ability to recognize complexity generalizes out to things that are not that system of the paracellular tomograph. And when you mentioned the interesting thing of water is that terrible to study because it is just so complex. And yet we as people intuitively recognize that water and ice are the same thing, but different. Well, perhaps that's sort of because of that generalization principle where there is enough complexity in the way that water is changing that we're sort of, the learning that we're doing is to just sort of, is intuiting that kind of thing.
Maybe perhaps the fact that water does have such a complex, was it phase? What was it called, Max?
Phase.
Yeah, phase transitions. Like maybe, it's not a coincidence that living beings depend so much on water, and perhaps what Christoph was saying. So, okay, one of my like feelings is that basically the way that you make models more robust is kind of by giving them baths regularly or like letting them have dreams. And that this is kind of like letting noise flow through them. And maybe like in the context of biology, maybe the purpose of water and all that memory that it stores is that, as we as observers move through the world, we accumulate junk in our bodies that needs to be kind of like washed out regularly. Otherwise, we like cross over into the too complex to persist side of things. And so we're kind of always trying to maintain this like delicate balance, between simplicity and chaos, and that water might be like a fundamentally important molecule for maintaining that.
Well, have you what Max was saying? Just to ask, have you read the Daniel Dennett's Real Patterns?
No.
It's a pretty interesting paper. Just to this.
No, I haven't read it. What do you want to maybe say a little bit about what it's about?
Well, it's about Daniel Dennett's viewpoint is about the complexity which emerges from its simplest of constituents, and what patterns can we count as real. So it's like one of the earliest papers in the complexity studies. It might be interesting to look at.
I have sorry.
I just want to say one thing about water before we move on from real quick. Isn't it kind of surprising that we are effectively living water and we never refer to water as something that actually has capacity for life, and yet we're like 70% water and we're just actually animated water, right? Think about it. Maybe it's not accidental at all. Maybe it simply is a molecule that's amenable to the kind of manipulation in 3D space, but the kind of process that we are the life, so that it's actually its memory is an integral component of a living system.
Yeah.
Yeah, actually, I just wanted to say, I was kind of blown away by the points that, Christoph, Bill, and Novak were making. I think that we've, kind of struck on this pretty profound point here, actually, which, I'd never thought of before. And it's just about water, really. I mean, people talk about this idea of emergence, right? Like having, Wolfram talks about it, his cellular automata, that people talk about, you have simple rules, and then out of these simple rules and simple things interacting, you get this complex behavior that you wouldn't have predicted from the rules. And I think, water seems to be a great example of that. Like it's one of the simplest molecules you could even imagine, elements, 1 and 2, or, okay, not 1, 2, it's hydrogen, oxygen, or whatever, on the periodic table. But the fact is that it has this almost like infinite complexity. It's incredibly complex, phase diagrams and all these phase transitions, and it's almost impossible to understand. And like emergence has to start somewhere, right? Like, it has to be there at one of these low levels. And I think that this was kind of a great insight that we've kind of maybe inherited in some way from this complexity of water. Maybe it's not a coincidence that we're water-based life forms in a certain way, that, this emergence of complexity from simple rules carries over maybe. But yeah, I thought that was very first.
Max, but can I propose a sort of like an experiment? Imagine for a moment, what is it like to be a Wolfram model? What would it be like to be a thing in the world? You have atoms of space, right? Like these pixels, they call the atoms of space. I simply assume that they have something that's just that does not have constituent parts, points, and you have relationships between them. And then when you're moving through space in Wolfram model, you're moving from one configuration of the rulette to another. So essentially, it's like a phase transition of an object that just kind of just goes like mechanically changes from one to the other. Like you're in this different configuration of atoms of space, right? So if you think about, instead of thinking about chemistry and molecules and particles in the 20th century physics model, where you have a bunch of little balls floating in space, and you think about it as a configuration of a graph that you're changing, that totally makes sense. That basically when I'm moving my body, what's changing is the shape of the field that generates my body. And that shape and water is just simply part of that field. That's how it emerges out of that, the only field that is the computational substrate of the world, what I call the computronium, right? Like the computronium is a proto-computational substrate. It has both geometric property. It has both geometric properties and has computational properties, and they're not separable. That's my model. So it's kind of Wolfram model and geometric model at the same time. And I'll tell you this, and I'm not joking here. So far as I can tell, I have a complete account of exactly the mapping between configuration space and geometry of the perceived reality. Like I know how it happens all the way. And I can tell you that I can see, for instance, a way of like understanding this phase transition diagram through of water. There is a way to map the trajectories through phase space, because that phase space has geometry. And once you understand that, once you record the trajectories, there's a way of turning that mapping into something that has actually structure that's visualizable, that can be made interpretable. And essentially that can be done with neural networks too. And it's all basically that based on this notion that general relativity is essentially all about causality. It's about geometry of causality, and quantum mechanics is about computation, which is also it's an causal evolution of systems in a step-by-step fashion, a phase transition. A state transition, right? A state transition is a phase transition.
Sure. It would probably just I think you would find I linked the thing she sent me down this rabbit hole originally as some work from Jacob Berander, who is I think very much in line with your outlook, and he's got a bunch of papers on there for everybody. Just wanted to point out, like, hey, there's some papers you probably would really like.
Oh, but I got to the point where I have an algorithm. I'm just implementing it, and I'll see if it works.
You might be working on the same algorithm that I'm working.
Yeah.
We all are, right? Like ultimately, people like us, we all work on the same thing.
I've had kind of a feeling, and I've been telling people in my company that I talked to about this, that like the surprising thing about this in the end that I think is going to be true is that the algorithm that gives rise to AGI is a very generic algorithm that everything in the universe is running, and like that it's not actually going to be something that anyone can like protect or like hold for themselves.
You know what was my starting point? Tic-tac-toe.
Yeah. That's
if you can derive,
if
you can derive a minimal model of observers from that.
Yeah.
If you can derive general relativity from that, you have it.
I was going to mention a paper that I think is related to a lot of the stuff we just said, this is not AI or ML paper, but it's by a group of mathematicians. So I had a professor as an undergrad who was well known in dynamical systems research, Mikhail Mizurevich. And he had this paper called Unpredictable Dynamics in Congestion Games. memory loss can prevent chaos. And basically they show that like you can set up this simple symmetric network, and it has like 2 or 3 parameters, and one of them is like a memory loss parameter, and it's that memory loss parameter is at 0, then you always have chaos where basically there are, you know, configurations of the game of any period that you want. So you can basically like find, you know, arbitrarily long loops that the system gets stuck in. But if you have like any small amount of memory loss in it, then you get stability. And so this is like in line with my whole feeling about this, is that like the models that we've been training in this industry for the last few years, I think are very, very close to the right thing, but we kind of need to like give them a bath.
But we are doing that.
To
Right? Like this is what this is. We trained the models. We made them work the first round, and all these companies race to develop tools internally for data sets to get better things. If you look at FineWeb EDU data set that Carpati uses, for instance, there are guys who are doing what they call the GPT-2 speed run, where you can train GPT-2 to on the FineWeb EDU super quickly to the loss of like what OpenAI got like 4 years ago. You know, on a H100 8 H100 cluster, I think we're talking about something like less than 3 minutes to get to the smallest models.
Yeah. I think training them on like lots and lots and lots of text is kind of like very close to this giving them a bath thing that I'm talking about. I actually think that you like don't even have to like, you can basically do the equivalent of like training them on noise for a little bit after you've trained them on whatever data you care about, or during training you alternate between I actually had this thought today of like that maybe we should be giving the models high intensity interval training, where you give them really dense text, you know, that's like the stuff that you really care about, followed by just a little bit of noise or whatever.
But
It's responsible for their cellular automata thing, right? Like effectively, that's just a noisy system that has the perfect amount of noise.
Yeah.
and so what if we could derive you know an actual estimate for exactly the amount of noise that you need to give the model? Because if you think about it, what we really want is for these things to be sort of self balancing. And there is a in the neuro literature, the rebus model for psychedelics, relaxed beliefs under psychedelics, is an interesting mathematical model that kind of tells you what do you need to do to perturb the energy landscape of a system in such a way that it can get out of its sort of like local energy minimum. You know, just you sort of flatten out the energy landscape so the system can get out of the energy minimum. And that's the sort of model for function of psychedelics. And I think, you know, this sort of, if you could estimate that quantity for the language model as you train it somehow, for understanding that you need to do this kind of normalization, you might be able to find places, first of all, that the model needs more training. So actually get some kind of introspection into what the model is not so good at. And secondly, it would tell you, like you get information to where, like, you know, what the model is sensitive to.
The other idea that I had was that you could like, okay, you train a base model, and then, train a model and then you do something where you basically, I was thinking of this as like allowing the model to have dreams, like basically where you randomly prompt it and allow it to generate text, and you're training it to predict its own output, but also like pushing back against that a little bit to like basically like combining that with some kind of entropy, some kind of piece of the loss function that pushes entropy up, where it's kind of trying to like float a little bit about just outside of the training data that it was trained on.
But let's just get back to the energy-based models here for 1 second and think about it this way. It's like you're thinking about what to do with a system where you have a model of a system. Like okay, so I'm going to have the model have dreams. So I'm going to do something to the system that I think will make it have dreams, right? So you are modeling in your head the system anyway. So you kind of have to do that. But from the perspective of the energy-based models, what that formula is, why these exponentials are so beautiful, what it is saying is that you can forget about all of it. That all of it can be understood, whatever it's happening, in terms of geometry. That's one way, and in terms of evolution of configuration, configuration space. So instead of looking for why the energy-based models are so difficult to train is that the sampling that you need for training is actually very time consuming and costly. That's a CPU bound process. And that's where like Max employer and I suppose Xtropic, have their value proposition. They're essentially saying that like, we're going to build devices that are very good at sampling from energy-based models, and that will actually make energy-based models, this extremely nice and general class of models, tractable. Now, what I have in my minimal model is a composition it's a construction that essentially is a composition that tells you what is the optimal way to derive a structure that on the one hand has geometry, on the other hand has a configuration space, and how that structure is a form of translation between, two different components of a system. So essentially, what you're showing is that, it's effectively, how to quantum systems communicating over a quantum channel necessarily create geometric structures in each other's configurations, and that's kind of like how space and everything arrives out of that. But this algorithm can be implemented quite directly. Like you can understand step by step in a quantum system what it actually means to evolve to the most optimal configuration. And you can do that very easily by simply having the quantum system model itself its own uncertainty about the future. So your refinement path integral happens essentially, in the space of counterfactuals too. So when I think about, I'm going to go get a coffee at Starbucks or I'm going to go get a coffee at another place, I am, evaluating counterfactuals. I am folding space as I'm doing this, right? So the wave function is evolving, and eventually there will be a snap, a decision will be made, a gradient path will be established between the configuration that is desirable and the configuration that's here. And then all that happens is the minimization of free energy as they go along. And, there are other people doing the same thing to the system, minimizing it as a kind of like a massive blockchain. But that can be understood quite precisely that you can build it at this atomic level where an agent understands itself, knows its own model, knows how to construct it. So if you have an agent that has a generative model of its own generative model, so it is its own model, right?
Yeah.
If you can build that, you get AGI.
Yeah.
No, but that thing is useless. It does precisely nothing except modeling everything. So you have to put intention into it, And where does the intention comes from, right? Like that's the thing. You're gonna find the intention is gonna say like, well, tell me what to do, and I'm gonna do the best I can to do it.
Yeah.
And then you're gonna find out, and this is where it gets funny for a lot of people, that there isn't, what Chris Langan, I'm a big fan of this guy recently, what he calls a global operator descriptor, GOD, right?
Mhm.
There's a global thing. There's a global thing driving the process, and essentially the thing that needs to be done. So that's what you can call the will of God, right? Like if mathematics tells you that this is the most optimal way to act, period, provably mathematically, and optimally you see it, you understand it, you feel it. It's an actual palpable feeling of geometry that this is the correct action. This is what's called the Zen mind in the Eastern traditions. Acting with the certainty that what you're doing is correct without having to think about it. It's an achievable mental state.
Yeah.
So, you know, what I'm essentially trying to do is to build a Zen AI.
So I just wanted to pause for a second because I thought that somebody else had something to say.
I was going to say, isn't that, yeah, the GRD thing, isn't that essentially what active inference proposes? Is that like the main motivation for agents to have intention is to balance their homeostatic processes, which is like the free energy minimization thing is a proxy for.
100%.
Cool. Yeah, glad to make that connection.
Gotcha. Interesting. Yeah. So let's like take a moment to reflect on EBMs, right? Let's just take a moment to think about energy-based models. And after we've gone through this, you know, kind of interesting and winding road of doing derivations and discussing, you know, some of the implications, like what do people think? Like why do we care about energy-based models? Like why bother? And I know we've already discussed this, but like I'm just kind of wondering if we can kind of summarize or encapsulate like what matters about energy-based models. If anyone has any thoughts on that.
I mean, we live in a physical universe and we have some idea of how it works. And it seems like a good idea to try to build, if we're trying to predict, you know, things in the universe, like what token's going to come next in a sequence or which action I should take. You know, it seems like obvious that ideas in physics should be relevant and that we should be searching for model architectures and, you know, training paradigms that reflect that and take like the idea of energy and energy conservation and stuff like that seriously.
I see. So that's kind of that's interesting to you. So it's kind of that like what you're saying is that like because the way that you know an input becomes an output in physics has to do with the laws of physics are governed by energy functions or Hamiltonians. If we want to learn this function from input to output, we should base it off of energy in some way. Is that kind of the idea?
Yeah.
Makes
And I
sense?
think there's probably like an equivalence between energy and information, basically, or energy and entropy, that they're just kind of like secretly the same thing.
Yeah, I like that. I like that way of putting it. That like, you know, somehow it's more efficient to learn things in terms of an energy function because energy functions govern the laws of physics. So if we learn in terms of energy functions, we're maybe taking advantage of some kind of you know, what's the word? I forget what the term is, but some kind of bias that makes it easier to learn that, you know, the real relationships between things.
Or universal compression algorithm. And brief having the way you would do that if it's a model and if even model or essentially anything where they're within the Riliad with a model, then you can arrive from arbitrary point A to
Yep.
But you know, I think it's fair to say that we study energy-based models like we specifically this group. I would venture to say that most of us do it because they're beautiful.
Yeah.
So I like that view. That's another view, right? That we, you know, purely for our own kind of gratification, right? Is that, and I mean, I don't really disagree with that. You know, I definitely do like working with energy-based models. So, okay. So we had, you know, Bill's view that like kind of there's this nice, oh yeah, that was the term, inductive prior. That, you know, an inductive prior is when you put, you constrain the way that your model learns. So it makes it easier for it to learn laws of the right form, kind of like a convolutional neural network or something. So I kind of understood that point as like energy-based models are like an inductive prior to make it easier to learn the real physical relationships.
Oh my God, sorry. Just an important insight related
Go
to
ahead,
our
yeah.
previous conversation.
Sure,
and
sure.
this and it, yeah. Remember when you spoke about Kolmogorov-Arnold networks? Is that they put the composition of function is what you parameterize, and effectively so the functions on the edges, right? With this energy-based function, what you're essentially saying is that because I'm going to use exponential, which is a function that has the same curvature as any function I ever want it might have, right? Is that universal basis function. So I'm putting all the complexity of the calculation into that operator, and all I'm going to do is to figure out how do I compose that, right? And if you were doing something else, like you could use a Fourier system. What Fourier functions are not necessarily good enough for capturing linear time invariant systems that physics are, because this is essentially what exponential function is. You're choosing a resolution. What you're saying is that I have a universal basis function that I know has the right properties for modeling linear time invariant systems because its shape, it remains unchanged. As a result of passing through that system. So, and I'm trying to model a linear time invariant system. That physics. It's a linear time invariant class models. I claim that's what physics is. So by specification, I arrive at this very good fit, that these models happen to be good fit for the kind of systems I'm trying to figure out, because precisely they are the kind of things that they're designed to be a good fit for. So it's really, really interesting to consider that. And Kolmogorov Arnold network is kind of like a view on that, you would basically say. So here, when you see this exponential, that's your edge in a network. And the Kolmogorov Arnold neuron would be like this X that you're it's a measurement of whatever you're integrating over. You can make these estimates.
Okay.
And so when you train the networks, I guess I will point out that those decay through in order to do the training, the way that you do that is you represent those as splines. So in theory, if we were to pick like the exponential and then equivocate that with a spline, and I guess if you were to because the problem with them is that they're too wiggly. And like transformers are good because they fit into that geometry and they don't get caught. And it's at least my 80s third grade understanding of them is that they get caught in everything, and that's the problem. But if you could perhaps give them the precise directions of where they are supposed to go such that they don't get caught on everything, then you might have something particularly rare.
Sorry, I just had another epiphany here.
Wait,
Just one.
before the next epiphany, I want to hear it. But actually, so Christoph, I know I think you have a lot of really interesting views on EBMs, and I was wondering if you could kind of if you were going to summarize in one sentence why you think that EBMs are important to study, how would you phrase that? Because if I were going to try to, and Bill, let me know if I get this right, but if I were going to recap your kind of thesis on it, it's kind of inductive priors from physics is the way I would put it. And so I was wondering, Christoph, is there a similar kind of catchphrase? Because I'm kind of trying to collect pearls of wisdoms here that I can encapsulate somehow. So I was wondering if you could how would you give us that short, phrase or sentence summary of your perspective on why EBMs matter?
They're capturing the necessary structure of reality.
Mm-hmm. Okay. Necessary structure of reality. Okay. Okay. Gotcha. All right. I like that. I see. Okay. Do you think that's how would you, okay. So to go into it a little bit deeper, how do you compare and contrast that to the inductive priors from physics, version of it, I guess?
So inductive prior from physics is, I'm an observer of the world. I observe the world and I write down my model as physics. And I know something about the nature of physical systems. I understand their evolution in time. I don't know what they are. I don't know what they're made of. I only know that how they evolve in time. That's essentially what physics allows me to do. Mm-hmm. So I capture that, and then I create a model that includes certain aspects of what I understood from the study of the behavior of the systems that I'm trying to model. Like, for instance, the relationship between energies. So I can write my Hamiltonian, and I can do the the evolution. I can minimize the gradients there and evolve my system into a ground state, right?
Yeah.
That is the first level of putting the right inductive priors, but it doesn't but it does not have the structure that's necessary to produce the model that the whole thing really is, because I am part of that system, right? So I'm putting my best estimate of the model. But if I keep going and I keep trying to design more general models that build a hierarchy of those, I will eventually arrive at the fact that the energy-based model is necessarily the most general model that it exists. And there's a because it captures a necessary geometric relationship between configuration space and real space, and that simply it's unavoidable. It's a necessary structure of reality. And if you understand how it's necessary, like the whole construction, where it comes from, the whole modeling process, it's not something that is not a proposition for me. Like I simply know it to be true in an inalienable way, because there is a whole formal system of thought on which this proposition is resting. Like I understand how I understand, right? And the statements that I'm trying to that I'm making about these things, a lot of them may sound fantastical, but I have precise estimates, of how much credence I give to them and the whole structures necessary to back them up. Like I know that I know how I know at all times. So that's how we see the structure as necessary. This is what Wolfram essentially, he arrived at this view with the Rule-Yet. You just simply accept that Rule-Yet is. It's not a falsifiable theory. It's not something that could not exist. It's simply a biological deduction. If something exists, there what must be, and energy-based model is essentially that. It is that if something exists, if this is what you assume, if something exists and can relate to itself. So I have atoms of space and relationships between them, or the universe folding upon itself geometrically. Then the energy-based model will be the optimal model for capturing this relationship. That's plain.
I think I appreciate much more your way of putting it, necessary structure of reality, after you said that, because when you first said it, I at first understood it as like capturing the amount of the structure of reality that is necessary to capture. But now that you said that, I think that it's more what you mean is that it's necessary that reality has this structure. Like there's no other way that reality could be, basically.
If I can pivot in a second into a very different direction, that I often talk about the Dhamma and Buddhism. And in Buddhism, Buddha says that at the end of the path, the bhikkhu will know that the Dhamma is the true Dhamma, that Buddha taught the Dhamma correctly, and that his disciples practice rightly. Because Buddha understood what it means to fully transmit a concept to another person. And this is something like that. Once you understand what it means to understand, you just, it flips the meaning of the word necessary around. For me, the necessary doesn't mean it's wheeled in. It's just a feature of the world that I'm trying to model. I know where it comes from. That's what I mean by necessary.
I see. So in other words, like when you say reality, like you don't just mean like kind of like what happens to be in the world as we know it, but more like this, like almost like Platonic form of, in order to have a logically consistent reality, it has to obey certain structures. And you're kind of arguing that the fact that we parameterize distributions by exponential functions is actually just something that comes from this, overarching structure that has to be there, basically, because there's no other way it could be consistent, kind of.
Yes. It's
I think there's also, I often think about like Gödel and completeness and what that means for like this type of stuff. And the fact that there's kind of always things in the universe out there that you like will never be able to prove happened or didn't happen, that are just like so far outside of your frame of reference, just means that you're always stuck with being forced to you have to be willing to update your model in the face of evidence. And like training these models this way is precisely this type of thing.
So it's like, it's an like when you model things this way, it's a direct acknowledgement of like the contingency of your frame of reference, basically. And that like what you perceive to be in your environment, you know, can never be fully known. And so you always have to be willing to update on new information.
Actually, there's a perspective. Go ahead.
But yeah, I want to summarize this for myself to see if I can get this here, because like the thing that is crystallizing for me is that that phrasing necessary is sort of working. So the Rubiad is all of the possible everythings with encapsulating the everything's encapsulated. And going all the way down from that, and getting to me is the position from which I am observing. Like things have to be the way they are because this is where I am looking from, and this seems to me, or like I think after I digest this or do some more digesting of this, and maybe we can do some the models, is I should be able to get from all the stuff down to the stuff that like the quantum observer that is like anchored in place, that is me, is capable to like be in the same state space as, which is sort of land. So like that's kind of how I'm conceptualizing this sort of necessary concept that you meant there, Christoph.
So no, that I think that was a really interesting thing to say, and I want to like go a little bit deeper into that actually, because so you said like things have to be the way they are because this is where I'm looking from, and in my mind there's like maybe different ways of interpreting that, and I think like for example like one way of interpreting that is the idea that of like you looking under the lamp for your keys, like if I lose my keys on a dark street, where should I look? Well, I should look under the lamp because I'm not going to find it anywhere else, right? So I should look in the place that I'm likely to find it if it happens to be there. So that's one way of interpreting it, is that like we should try to construct models of reality that we may be able to understand. Now, even if that's not the best model, the other way of interpreting it, in my mind, is that our theories really are not about nature or about us, but about the interface between us and nature. That's what our theories are about. That's another way for me to interpret what you said there. So I was wondering if you thought that one of those interpretations was what you meant, or something else, or yeah, if you would just expand on that a little bit.
Yeah, I think the second one is closer because it's it's less that there's a difference between a street and a light, and it's more that like there is this morass of things and not things and concepts and not concepts, and that morass is passing through the object that is me, and I get to process that in the ways I get to process that because that is what my processor is capable of processing, kind of. And the things that are become conceptual to me while I do that processing, those are the necessary things. But they aren't all the things, or they're not necessarily the right things, or even good things. Just from the position, I arrive at this collection of things.
So what you just described is captured in Buddhism under the label of dependent origination. What you're saying is that you are the way you are because you interpret the world the way you do, which is the way you interpret the world that is because of the way the world is, and the way the world is because of the way you are. So that kind of completes the circle of generation and interpretation. Is that at all? Yeah, the Buddhist view is that consciousness at all points is optimally positioned to achieve liberation, and if your circumstances are disagreeable with you, that's the loss signal, that's suffering, that you need to move from the space where you are in to some other space where you are not suffering. And that move, that path, the following of that feeling, that minimization of suffering, is the free energy minimization. And that's what Buddha called the Dhamma. But, so we're talking about like a lot of these ideas. There's an intellectual understanding of them that, you can talk about it conceptually. You can write down some mathematics and you can say like, well, yes, there's a mathematics to it. I understand. But there's also a dimension of understanding here that's required to fully grok the model. It's a different form of understanding. You just simply start to see the geometry of it. It's a new sense of it, almost like a spatial dimension. And I'll give you an example. At work, we're building a computational language for expressing structures of computations in terms of the sort of like interesting composition of data flow and control flow. And we have a diagram language to do. And the diagram language is two-dimensional. And I was attending a presentation, and one of my coworkers, just had these two-dimensionally laid out diagrams with a bunch of links, but it just popped out in my head in 4 dimensions, actually. Like I could see how this is a folded structure where there is a spatial relationship that is overlaid on a temporal relationship. In other words, I did something akin to, metric tensor transformation from something that appeared flat, but had a folded structure, to something that appeared folded, even though I was looking at the flat image of pixels on the screen. But the crazy part was that I was not only aware that I was doing it in the moment when I was doing it, like I just simply saw the image and I knew how I'm constructing it. So, the reason why I'm excited about all this, and I talk to people, always bring up this weird Buddhist spin to it, is that it's not a theoretical idea. It's something that you learn to feel. Those energy, that thing, the force in, Jedi lore, it's actually a palpable thing that you can just learn to feel. But all you have to do that is to learn to stop for a moment and do nothing.
Yeah, so I've been thinking a lot about this same stuff. Okay, so there's like 3 little snippets that I kind of want to tell you guys, if you're willing to hear me out, and I'll try to just keep it short. So number 1, to keep on the Buddha subject, is one of the things I've realized is that like basically what happens when you practice mindfulness, if you're doing it whatever correctly, if you can describe it that way, you're letting your mind settle into a low energy state and you're watching information pass through it. And the flip that happens eventually is you realize that you are just the space that it moves through. Like you are the wormhole. You are not the thing moving through the wormhole, right? Like you're this network of things that are connected that information just passes through. And so you can just like stop and just be. And if you get really good at that, you can basically become pretty disciplined at letting that noise settle down. And then you will enter this like very low energy state where you feel this kind of, nirvana feeling or whatever. I feel like this has some like implications about even like, the whole like way that we talk about like the tech singularity coming and accelerationism. Like I was kind of like, I guess I would call myself a like cautious accelerationist. And now I have this like egrad thing in my name for this reason. And this has been like more confirmed by like more recent ideas that I've been thinking about. But basically that like, if you take Einstein's happiest thought seriously, that acceleration is just gravity, like there's kind of, acceleration is like kind of just like in the eye of the beholder. And
the way that you actually like exercise real agency in the world is you like slow down and grow your network. Like you slow down, you learn to pay attention to what's directly around you really well. And then you can like use that to grow your network outward in many directions at once. Whereas like, and there's you can mean a lot of things when you say accelerate, but like the idea of like wanting to get in a car and slam on the gas, right? Like what actually happens if you want to maximize acceleration is, you're going to be in your spaceship and eventually approach light speed, and then you're going to hit some particle that rips your ship apart. And so like in some sense, like staying still, paying attention, growing your network is like the wise takeaway of all this, in my opinion, which is very like in line with kind of Buddhism and, a lot of this like Eastern philosophy. So that's number one.
So actually, yeah, just
One comment on this.
Sorry, no, because I really like that phrase that like acceleration is in the eye of the beholder. And actually, I thought that the connection to GR was actually pretty good there. Actually, it was a nice connection because in the big thing that the world shattering revelation of general relativity was that not only is velocity relative, which everybody knew that v was relative, but a is relative. Acceleration is also a relative thing. It depends on your reference frame or what gravitational potential while you're in. So I thought that was an interesting way to phrase it, that acceleration is in the eye of the beholder. But I was wondering if you could just like expand on that, and like as it relates to like accelerationism or like EAC or whatever, like how might people have different perspectives where what for one, what something that might be acceleration for one person is not for another.
I think like basically
just one quote. Just one quote. Sorry, like one quote to we are a still point in the turning of the world. T.S. Eliot. There is something to.
All right, thank you for
yeah,
that.
for sure. I don't know, like Einstein's happiest thought, basically he says, right, like that if you're a free falling observer in the universe, you actually don't experience any like acceleration. And this is like almost like just the same thing as like what mindfulness is, and like what you're supposed to kind of realize if you practice mindfulness is that like you can just like sit still. It's also like it feels not a coincidence that it's called Einstein's happiest thought, right? And that like meditation is in some sense like a very easy way for like anyone, no matter their circumstances, can practice it and like experience happiness wherever you are in the universe. That like that you can alter your own frame of reference. You don't have to physically run as fast as you can in one direction or whatever. I think on like accelerationism and EAC and like the political side of this stuff, it's that we should be really careful as like a civilization about if we start doing something where like society becomes very one-dimensional. Like for example, if we go to Mars and then like form just like a really angry war between Earth and Mars that's like very one-dimensional, that's like probably a way that we could actually like get into like some kind of civilization destroying war or something. Whereas like growing outward gradually, making sure that the bases are covered as we go. And I'm not like one of these like we need to hyper regulate AI or anything like that even. I'm like fairly libertarian, but it's kind of like made me reassess my own like thinking about this stuff of like, I don't know, be a little bit more careful than just like aiming for the stars, if that makes sense. And shooting as fast as you can toward the stars. Like a wise civilization is one that will like gradually grow its network thicker and thicker as it grows outward, which I think we can and will do.
But to bring it back to energy-based models, consider what the energy-based model formalism is really telling you, together with the Schrodinger equation, because they fit like the exponential functions. They're just kind of like they are essentially saying the same thing. The Schrodinger wave function is an energy-based model of the universe as a whole, and it simply what it says is that the universe is evolving smoothly towards something. So whatever is happening, like worrying about this idea that like we should do this, we should do that, we are already doing whatever is optimal.
Yeah.
It's important to express the opinion that, in my opinion, the course of action is this, because the direction is set by beliefs of people, not what the correct course of action is. So it's important to be able to say, like, I believe that the correct course of action is blah, but the world as a whole is already running this optimization process that, in some sense, it is tending towards optimality. So Einstein's happiest thought was basically it's kind of like a Taoist moment where you just let go and you flow with it. So what this is essentially saying is that from where you are right now, there is an energy gradient that takes you from your circumstances in the most optimal way, taking into account everything else that is going on in the universe and all the agents that are interacting with it. And that gradient can be approximated pretty well geometrically through a class of functions. That is essentially what the energy-based models are saying. But there's a different view on all of this that you can adopt. You can flip yourself inside out and say that, well, okay, what if the universe is just simply evolving and it's a system that I have no access to other than the only thing I'm doing is sampling it, right? So my life experience is the universe is evolving and I'm just simply sampling it and I become conscious of it. And at never point I'm a decision maker. I'm just simply an observer. That's it. And then you can see essentially this from the quantum perspective. The energy-based model is your energy-based model is a smaller version of, say, the universal energy-based model, but they're isomorphic, and it's essentially it defines how aligned your reference frame is, your internal reference frame, with the universal reference frame.
Yeah.
Like the universe will go wherever it wants to go. And you can go for the ride, or you can, in exactly the way, God orders you to go, or you can suffer if you have an unaligned reference frame. It's a change in perspective, but it gives you a different view of what this model really is, what those weights are. They're pixels. They're the pixels of your holographic screen.
Yeah. Yeah. I wrote this down like a long time ago, where in the process of sense making, was the other thing that's sort of occurring to me with this is that since we have those equations that are effectively the through line through the whole thing, and we have these, like, we have all of the math that we can do, and I am like a thing that is doing math more or less. What would be meaningful, or what would meaningfully change my perspective, would be to change the position in which I am encoded, right?
Mm-hmm.
And then subsequently, everything that is also has that condition. So it's like a turtles all the way down situation.
Yes.
So in that,
I think of it as like a bunch of turtles on a sphere next to a big three-dimensional sphere. Turtles you're packed in spherical packing or something.
well, compressed turtle, right? Because that's that's
Mandelbrot turtles.
yeah. And so like it like I'm all I'm doing really is like being at a particular position and squishing something into it and encoding. And so are my model, and so is like finance, and so is
Markets,
so is markets,
lives.
weather, and so and
Oh my God.
it's to be the thing, because if it's not the thing, these equations don't work.
I just had the realization when you were speaking on another epiphany, but I was thinking about the Mandelbrot set. You know what a Mandelbrot set really is? It really is a depiction of stuff that's outside of the realm of processes that have linear behavior. Right? You're saying that if I have a function that if I can just keep squaring the number, right, it stays within the Mandelbrot set, and otherwise it's out of that set, so it grows somewhere, so it goes somewhere. So what you're saying is that, like, what is the shape of things, of all the possible things that I can do that are within my computational cognitive cone, right? So it's like a sphere. Is like
Cognitive light cone.
yeah, a compute. Well, yeah. So I would call it a computational light cone. So, because quadratic processes that like they're growing in a kind of way. So what are the things that don't make more space in a way? It's a very interesting geometric interpretation of it.
Well, you can
But,
also think the square function. It's not just like you can kind of like reframe it and think of it as like you take a thing and you act. It's a thing that acts on itself by multiplying it to itself, right?
yeah,
Want to point out here is that it doesn't go both ways. I can go all the way up with the Mandelbrot set fractal, but when I go all the way down, I will hit something that we represent as like Planck's constant. It's the smallest. There is a lowest fidelity, but there isn't a highest fidelity, which is just sort of an interesting thing that came to mind.
I think
that's really interesting.
I'm still definitely undecided on how I think about that. Like that, if Planck's constant isn't actually like a fundamental limit of the universe, but maybe it's just a fundamental limit of the stuff that we are built out of, like of the substrate.
Oh wait,
It's an information theory. It's an information theoretic phenomenon, right? Like the Heisenberg
Yeah.
uncertainty principle is not a physical phenomenon. It's an information theoretic one. It's an interplay of your model making ability and the world.
I have two. So
right. It's the thing I get to swing around. Right.
yeah, I have two other snippets. Okay, so one directly related to some of the things that were just said. This is a thought experiment, or like, this is a little thought experiment that I got really excited about, and I need to maybe like Google more or something and see if anybody else has like pointed this out. But okay, suppose that my theory that like AGI or general intelligence or whatever you want to call this thing, consciousness, is like networks of wormholes, right? Now, this gives a really this is like a super interesting reframing of the double slit experiment. So in the double slit experiment, when you put two slits in a screen and then you shine light through it and look on the screen on the other side, you see this wave pattern, right? And if you set up the experiment where you're trying to detect which side the photon went through, you end up collapsing the wave function, right? Well, I think that, so there's two things. So that's like the known explanation of what happens when you perform this experiment and you try to actually detect it. But when you add slits, has anybody ever like looked this up or like read about this? What happens when you add more slits to the experiment?
Great. Or I haven't.
So when you have one slit, it's just a Gaussian distribution on the other side. But when you put two slits, you get this wave distribution. There's this interference pattern. When you add more slits, the interference pattern becomes more complex. And as the number of slits goes to infinity, it becomes a sequence of delta functions, basically. And so my claim is that the two slits are like a pair of eyes of an observer. And as you add more slits to it, you're making the observer more and more complex. And that's what collapses the wave function, is like the more observers that are participating in the experiment, the more certain the outcome of the experiment becomes. And what we are as like, biological humans is a giant fucking network of observers. So it's like a bunch of slits in the universe that information is, flowing through. And because our networks are pretty complex compared to two slits in a screen, that's actually what leads to the collapse of the wave function.
And what if you could, as I referenced for fumbling in the rabbit hole I fell down, was what if you had a causally local formulation of quantum physics? What if you didn't have a wave function? I just linked the paper and put it in the Jumbotron.
Yeah, I think using like the Wolfram Ruliad ideas, like you can kind of formulate this all as like something that could run on like a big computer using discrete bits, and that like a lot of this stuff, yeah, like the non-locality is in another sense just like the fact that we're made of multiple things, right?
Can I say something about the wave function collapse?
Mhm.
What is a wave function collapse really? Like there's a wave function that's evolving, and I'm an observer of the wave function, and I am the wave function, right?
Right.
And at some point it hits a situation where effectively a pixel has been computed. Like that region of space contains the computation that's bounded in a very, very specific way. Like there's only one outcome that's possible. So it collapses. Like I collapsed it. My, like essentially it's like it's been detached. It's been contained in such a way that it collapsed into this quantum particle.
I guess
So you have
the way
this-
I think about it is almost like you as a very complex biological observer have such a complex energy landscape that like as that wave passes through your body, it interferes with itself a bunch of times, as it's going through the different neurons and, your
yeah,
body or whatever.
but at all points you have to think about one thing, that I don't know what I am. Like I experience myself as a biological thing, but biology is just a word I denote some kind of state with, and that's a mental state in the first place, because what I am experiencing is the generative model, not the world. So the only thing I can say is what my screen looks like, and keeping that in mind, that the only thing I can say is what my screen looks like and what the mental structures that are producing that screen are like. You can climb that hierarchy going upwards. Like you are thinking about this in terms of I'm an observer studying the world, but you can go one step upwards from here and now, and you can say like, well, what if I apply the same principle that I now understand are universal for the description of what the screen is, what the things on the screen look like, right? So I have a theory of the behavior of the things on the screen that I claim is complete, and then I say like, what if I apply that theory to the screen itself? Can it explain to me how the screen is created? So how is the model making process making the model? Right? And then you can build the structure upwards in your mind, which is the kind of what I would call the meta mindfulness, because you're not mindful only of the energy of the changes in energy landscape. Only you are mindful exactly of the transitions that they cause. So the causal nature of the transitions in the world is established, and you're always aware of both. Meta mindful of the causes and mindful of the evolution of the system, and that translation between causes and effects, that is the universal function of a neural like architecture, where you have this spatial temporal evolution of a system, and at some point you can think about it statically as a kind of a geometric object that's doing compression, that's translating one space to another, but apply that to the network itself and its own structure. You can go in and at all levels, it has to be self-similar, because it's the same thing. We're talking about universal basic blocks. So another thing that we are talking about, energy-based models, why they're interesting to study, is that we should be able to make them compositional. So I should be able to simply say like, look, I can give you a better model for your eyes. Like I can give you better software that, given the photons that are hitting your eyes, I know for a fact it will, extract more information out of that data, and it looks better, right? It produces better image in your mind, so to speak. That's how compositional they should be, because exponential functions are like that. You can always just kind of match them because they're always smooth and continuous, both in their value and all the derivatives in all places. If you use the right building block, you get the right properties by construction, right?
I just thought it was cool to think of the double slits as eyes.
No, you're totally right, because like you have a projection from configuration space to the outcome space,
Mhm.
and you're collapsing it, right? Because you're only on one side of that space.
What were you gonna say, Yikes?
I need to say, and then we get back over to ADS-CFT, which is like, okay, like what happens when you look behind that screen, and what are the rules there?
Mhm.
So that kind of like anti-geometry, right? Like this geometry of this anti-geometric space.
Yeah, I don't have strong opinions about that. I studied.
I just learned about it like 2 days ago.
Yeah, no, I think ADS, based on what I read of ADS CFT, it sounds like it's probably true. Like that's what my gut tells me. And it's really cool if it's true, but I don't have the math physics chops to have like a super complex or well-formed opinion about it. The last thing
Yeah.
the last little rabbit, I wanted to mention one last rabbit hole for you guys. Oh yeah, maybe not the last one. This was the
Yeah, guys, this is the last one.
the first one was the Buddha stuff and meditation and general relativity. Second one was double slit experiment. The third one, and I'll just like kick you guys in this direction, is if anybody hasn't read about mycelial networks and fungi before, you should absolutely take a deep dive down that rabbit hole.
Next rabbit hole after that is zero knowledge proofs and how they relate to those networks.
So there was something I wanted to say actually. So I thought that yeah, the idea of like the many slits and like how when you in the limit of like having infinitely many slits in a screen, the the wave function at the limit of having infinitely many slits in a wall, the wave function at the screen past the wall becomes a series of delta functions, and that maybe that had something, that was like an analogy or maybe even not just an analogy, but a model in a way for like how having many people observing something kind of collapses the wave function in a way. And I think that like, so that's in a way related to like historically in quantum mechanics, one of the big kind of schools of thought that happened, I think kind of in the 70s and 80s was what was called the many minds interpretation, which is often kind of like distinguished from the many worlds interpretation. It had something to do with having like, many people together, like kind of observing and understanding the universe is what like collapses the wave function or something like that. And it was very like kind of provocative and interesting idea. And a lot of people like studied this, but it ended up, I wouldn't say the many minds interpretation failed, but it failed to like lead to new theories or experiments or things like that. And there is a lesson in there somewhere that like it was something that it wasn't clear how to formalize, and a lot of people looked at the same thing but somehow had different understandings of it, almost like a Rorschach test where like everybody heard this idea of the many minds interpretation. Yeah, like kind of like that. So it was something that like it was somehow it wasn't quite concrete enough, I think. But not to say that. Yeah, go ahead.
This is you're spot on, and I can tell you why. Because the many worlds interpretation, if you really want to see it
I'm
for
talking about
being true,
many minds interpretation.
many minds interpretation. If you want to see it for being true, and I believe it is, it's essentially my view. You have to have a complete model of mind, because
Yes.
for many minds interpretation to work, you have to understand how the world as you experience it comes to be as my experience of the world as I experience it to be. So you have to have the patience for me to describe to you how I see the world. I have to give you enough information so you can actually make sure that the meanings of the words that I use is something that we share. And then you have to be able to reinterpret your experience of the world in terms of everything I said, in terms of that my experience of the world is like. So if you complete this, it's a zero knowledge proof. Like if you give me a zero knowledge proof of some sort, then I will know that you know that I know that you know that I know. And that's that's why it was so difficult to find. It requires a precise model of observers. And what they didn't have is active inference. The move that you need to make in order to make it possible to work, what physicists have struggled with and are still struggling with, is they're stuck in a paradigm where they don't understand that the linear time invariance is only a proximate property of the world. It's not true that physics is like that. It's only because we study systems in as transitions between ground states that approximation is allowed. And if you're not studying systems in close to equilibrium, you're studying systems far away from equilibrium. You need to you need an additional modeling that can be captured probabilistically, and that goes back to the Markov idea that you can trade computation for space, but you can only capture that sort of probabilistic.
You're losing me here because okay, so you started off by saying like at one point you're saying like you know so you know, as I'm sure you know, all of our field theories are linear, or right, like on the quantum state, but but when you say like that we can't, like the LTI, you know, linear time invariance is just an approximation. Are you saying like we're gonna have like ultimately there's like some nonlinear Schrodinger equation or like the field theory basically, or?
Well, the Schrodinger equation explains the evolution of the system as a whole, so it's linear, right?
Yeah.
But it also has to explain an evolution of any sub part of that system as a whole, because it's right, because it's part of that system. But the evolution of the sub part of the system, right? If you look at it from that perspective, is missing information, because its linearity of its evolution depends on the rest of the universe, which the sub part of the system doesn't actually know. So what I'm saying is that even though the universe as a whole is a linear time invariant system that evolves linearly, you as an observer within the universe necessarily have to perceive a probabilistic structure. Right? So that probabilistic structure that emerges as a necessary condition, as a necessary consequence of the fact that you are an observer embedded in the universe, and observing the universe. So by being an observer, you have a Markov blanket around you. So there's a set of states that's separable statistically from the rest of the universe that constitutes you, versus what constitutes the universe. So what I'm saying is that that's the important move that you need to make in order to be able to finally make the translation between one quantum reference frame to another. And that's the tooling that physics didn't have.
Okay.
That's first in 2009, right? So that's really recent technology.
Right. So by the way, yeah, if anyone's curious, the kind of area of study, I guess, of understanding like how do you take a quantum system and then study a subsystem of it, that's called open quantum systems, which I basically studied in grad school, and there's a great book on that by Breuer and yeah. Well, if you just look up Breuer open quantum systems, you'll find the book. But it's so that's definitely like probably the most kind of active direction in like quantum thermo is studying like open quantum systems and like what happens when you marginalize out all the environmental degrees of freedom. But so I think that's a good thing to talk about. A point I wanted to make though was that at one point, Christoph, I think you talked about like in relation to this like slit experiments thing we were talking about. You mentioned like, well, what if we had a model that explained how the screen got to be there in the first place, right? Like we're somehow we're by compartmentalizing too much, we're focusing on one thing at a time, but we're missing out on what's really important, which is like having this interconnected theory that explains how the screen got to be there and also what interference pattern and everything at the same time. Now, what this kind of reminded me of, and this isn't like any kind of rigorous argument, but what this reminded me of was my advisor used to tell a story about a guy he used to work with. And my advisor, Dan, he was a cosmologist. So he studied cosmology, the history of the universe, how its metric tensor evolved over time, how the Hubble constant changes over time. And what they study in cosmology, which is basically using a theory of general relativity, is they take some gauge, because in general relativity, you have a freedom to choose a gauge. And what that means is that you can change the actual form of you can change the way you calculate the metric tensor, which is this matrix that describes this, the way you measure distance in space time. You can change the way you calculate that in certain ways without actually changing what the theory says. So you have these like the theory has these ambiguities in it that you can change the numbers in a certain way without actually changing the predictions you would make. And so that's what gauge is a certain choice in that ambiguity, like committing to a certain perspective, a way of choosing your metric tensor. And there's a number of many different gauges. There's Newtonian gauge or conformal gauge. And my advisor, Dan, he used to talk about a colleague he had who was a brilliant theorist, and as good as anyone, who had ever worked on GR, maybe as good as Einstein, I don't know. But the guy would never choose a gauge. That's what Dan, you said, the guy could never choose a gauge, and he had to try to write everything out in this formalism that would be completely general and would be able to capture any possible perspective that anyone could possibly take on the thing. And the problem was that the formalism that he ended up writing down was so complicated and so inscrutable that it never actually really led to any new results. And it was always just an effort to try to re-summarize work that had already happened, 20 or 40 years ago. And when there were new results, which there might have been, nobody could understand them. And I think the lesson there to me is that physics is actually, it's about making commitments at some level. We have this loss of innocence, right? Because we start out saying like, what are the answers to these big questions, and can we ponder the big questions? And then at some point we have to make commitments to certain ways of grabbing the world. And if we don't make commitments to grab the world, we'll never learn about it. We'll never understand it. So we have to sacrifice generality. And what we gain in return for that is we get the power to describe nature, and we get the power to predict. So yeah, I would just
let me point out that that you can commit to the I will understand it all. Just commit to it and say like I will do it, and the universe is going to be like, no, you won't, and it's like I will. Just watch me. This is the adventure, right? Like God promises you an adventure, and all you have to do is to choose it. So I choose the adventure. I'm going to understand it all. I'm going to commit. I'm going to go all the way. I'm going to remove all assumptions, including the assumptions of how I model the world, right? So there is a path that leads there, but there's the saying that mystics swim in the same waters that insane people drown in. That's the kind of trade that you're trying to make. If you don't commit to anything and you're trying to look at the most general system, then you have to understand that you will have to understand yourself inside out, and that is something that is psychologically not insignificant. It's not for the faint of heart. This pursuit.
That reminds me of another thing that I realized. This was like a month or two ago in math that I feel like is pretty deep, and I have never heard this before. So, do you guys know what the axiom of choice is?
Yeah.
So I realized that the axiom of choice, basically, if you look at its consequences in a bunch of different fields of mathematics, let me just list them before I give you the punchline. So the axiom of choice is basically that every collection of sets has a choice function, right? You can make a choice. In category theory, it says every category has a skeleton. In graph theory, it says every connected graph has a spanning tree. Every vector space has a Hamel basis, which is one where you can write any vector using finitely many of the basis vectors, even if it's infinite dimensional. Every set can be well ordered. Every topological space or manifold has a partition of unity. And then in game theory, it also gives rise to the existence of Nash equilibria in games. And I realized that every single one of these facts is basically telling you that you can do compression. You can start with some object that's fairly general, like a category, and you can basically use the axiom of choice to find its skeleton, which is like a compressed representation of it. But you have to make the choice. I don't know. I feel like
So think about the philosophical flip side, because it's an important one. Is that it's the choice to make these things exist that gives them reality. right? So it's an axiom of choice. I chose a direction somewhere in a space, and then you compute consequences. That's what that's part of like how you do mathematics. You create a structure. You define a formal system and say like, well, I have a constant zero and a successor function. What can I derive from that? Can I derive a model of arithmetic for it, and so on and so forth. So I make a choice. That's one way to look at the world. It's a constructive thing. But now that I made a choice, the choice has consequences. And that's the theory that comes out of the choice. It's the story that that choice leads to.
Yeah, exactly. So right. So the axiom of choice, right? Roughly speaking, you have some infinite collection of sets. It could be uncountably infinite or whatever, and you're allowed, if you accept the axiom, you're allowed to construct a set that contains exactly one element from each set in this collection, right? Now, every proof that uses the axiom of choice at some point says choose one element from each set, right? It says because of the axiom of choice, we are allowed to choose one element from each set. And so let's do it. We'll choose one element from each set. And then that proof will continue on and talk about what they're going to do with those elements. But at some point, they use it as a verb, as an imperative, choose one element from each set. And I think that's the point there, that you have to do it. You have to make that choice. Because that's what the axiom does. It allows you to make the choice, and you have to do it. I think it was a very nice thing to bring up, actually, is the axiom of choice.
But think about it this way, that like, and the problem obviously with that is that you have to choose what's the element of a set that contains all the sets, right? So that's how we find an axiomatic issue with axiom of choice, and there are entire set theories that are built on top of those that don't have that problem. And
Right.
it can be certain. But hold on a second, just 1 second. The modeling problem here is that you haven't put enough smarts into the container. So the set, this concept of a set is just simply insufficient because the set doesn't model itself, right? So if you think about the theory of observers, in some sense, a theory of observers is a theory of those kind of choices, except the set itself is the one that is doing the choosing. So there is no problem with something like axiom of choice because the observer is the observed. Like you just simply have to go to a system where you don't make that distinction between any component of it. The system is the system. That is the only object of the system is the system.
Well,
don't commit to it. Don't commit to any gauge. So what can you get out of this? Well, you get Roolia, and you get into circles, right? So how do you make a useful prediction out of this? That's the question that you were asking earlier. Like, can you give me something that it can? Can I give you something, in the real world, a tangible proof of the fact my system can do something that your can't?
That's the thing. You have to compromise, right? Like you just said a minute ago that like the concept of a set is not sufficient, and it's true that like the axioms of Zermelo set theory may have some aspects that are not completely satisfying to many people and many theorists even. But it's not quite right to say they're not sufficient because there actually are sufficient to like prove a great deal of things, right? Like starting from those axioms, you can come up with a lot of proofs and you can build out that ends up being useful, right? So
Max, yes, that's precisely the point. Have you ever seen the conversation between Donald Hoffman and Stephen Wolfram on Hoffman's ideas?
No, I don't think so.
So Hoffman has this notion of communicating Markovian observers. So he says, like, I'm going to model the reality as a network of communicating Markovian observers. And that conversation itself as a meta event was a very fascinating phenomenon because what they said was that this is what Hoffman was explaining to Wolfram. And Wolfram is saying like, no, you should go full computational. Why are you constraining yourself to using this Markovian model? And I wanted to scream on my screen when I was listening to this is that precisely Hoffman is doing that. He's making this choice consciously. He's choosing a model because it allows him to compute deeper than having the most general computational model, right?
Yeah, exactly.
What I am trying to point out is the process of choosing that model, the understanding that you are making this choice as a modeler.
Yeah.
Right. In my theory, I am modeling that as well. It's part of it. It's within the theory of how I make the choice.
Yeah, I've been wrestling with like over the last 2 years as I've been kind of trying to like chase down this AGI idea. I've thought a lot about like different architectures, and one of the conclusions that I've reached is that there are probably like a bunch of different sufficient and equivalent ways of setting it up that are basically like, doing the same thing, but just like they have different frames of reference, right? Like I have this idea that there's probably a way to build a model that's kind of in vibes based on like each of the like three main branches of physics. Like you could have a general relativity version of AGI that I was like thinking I would call like the transporter, like a wormhole, transporter thing that's all about like changing frames of reference. And then like a quantum one where it's more about like quantum states and stuff like that. And maybe like thermodynamics is like diffusion models, right? But that they're all like doing the same thing underneath the hood, and they're all like kind of in some sense mathematically the same.
Yes, that's but there's one thing that these things are missing, and it's the binding, right? So you solve the binding to the substrate, and you create a system that's just bound through either physical process, like Max and thermodynamic people, they might actually provide that kind of process that might be sufficient alignment between the a universal reference frame, which is like some physical process that goes on in the world, and the ability to influence it through manipulation of the natural world and the computational space. If the binding is sufficient, then essentially you have this automatic binding of neural network to the world. So that's one way to do it.
Yeah.
You can do it through hardware,
AKA
or
bound.
yeah, and I'm trying to do it algorithmically, to have a neural network that algorithmically, so to have a system that's not just a neural network, it's a system that comprises of a neural network, or it has a neural network like a computing capacity, to have a system that actually knows how to optimally bind itself to the environment. So figure that from first principles, what it means to actually figure out that binding. So I'm a quantum system abstractly, observing the world as a evolving quantum state. And believe it or not, I actually have a way of imagining what it's like. And like I'm being bombarded with information through my interface, like a modem is being sent some data. How do I figure out what the hell that stuff means if it's being sent by aliens? So that's the general frame that I'm assuming of, like, how can I say, like, what can I do as an intelligent, dynamic, adaptive system that is seeking evolutionary fitness within that framework of assumptions. So that's one interest. The company I'm working for instance, we are assuming that you can capture high dimensional geometric properties of computational processes that are related to reasoning in graphical structures. And you can use that for decision making in a complex decision making scenarios when an agent is, given some problem to solve, like a complex mathematical problem, and it can actually understand from the geometry of the problem what are the mathematical tools to automatically help it to build the tower of abstractions it needs to complete the task. So introspectable composition of general computational structures compared geometrically. That's the idea. It's a pretty groundbreaking way to look at AGI. And all of these things are kind of like, they're gonna kind of do the same thing, as long as you solve the binding. So, the simple binding for a lot of people is, while true, run neural network, do what the LLM says. That is a crude binding, but it is the binding, right? It's the same kind of category of the problem that we are dealing. And understanding that precisely how that happens, that is the road to understanding what physics is.
So I mean, my view is that we have to divide and conquer. We can't understand the mind and machine learning and physics in one fell swoop. And try, and people are trying. Believe me, it's that's not how it's going to happen. Like in my view, I
For
think
me.
that the way that theories develop is that people ask themselves, what is the low hanging fruit? Like, what's the next step that nobody has done yet? and people who, people who are really good at this are able to figure out what the lowest hanging fruit is that's actually important fruit, and they eat it, right? Um, and then there's a lot of people out there eating fruit that isn't important, or it is actually bad. But you have to think about it in that way. I mean, Christoph, you could be right. Maybe we don't have to compromise, and we can just think about everything we want to understand, and it'll all come together, and we'll get this one model of one understanding of the universe that includes ourselves, right, and includes our cognition and quantum mechanics and general relativity. But my opinion is that you have to let go of something if you want to understand something, and it actually kind of like radically letting go and seizing on to some very simple model of a very specific thing is like a really kind of liberating thing to do, actually. And that's what Einstein did. That's what Feynman did. Is if you look at Einstein's work, he always seized onto something very specific and came up with an absurdly simple model of it that was so crazily simple that people who thought it was just nonsense, but it ended up predicting the most fundamental aspects of that one phenomenon. In some sense, the only productive thing we've gotten out of quantum mechanics today is the laser, right? That's the only product that people sell today that actually uses quantum physics. Maybe solid state drives. Okay, solid state drives and the laser. I can't think of much else. And that was Einstein was the one who came up with the model that predicted lasing, and it was based on the most simple math that you could even imagine. Just a very simple Markov chain with three states. So that's honestly the way I see it, is that we need to let go of these aspirations sometimes and just seize on
And
very simple.
you're 100% correct. It's all about letting go. And that's how you arrive at the model of everything, when you let go of everything.
All right.
Yeah, I think the way I do think that there's kind of a unified model of everything, but then like the punchline is that, okay, if you have, as an observer, want to go use this model in the world to go understand something, you have to choose like the tokens that you're going to use to describe that thing, right?
Yeah.
You have to, that's what the binding problem is, right? If you want to study music, you have to decide what your language of describing music is going to be. Or if you want to go, study car traffic patterns or whatever, you have to like decide what your tokens are. Like, okay, you have cars and people driving in them and stoplights and intersections and stuff.
Oh my God. Can I just riff on this for like a couple more minutes?
Sure.
Please go ahead.
You guys, because like I have two perspectives on these things that are never separate, and it's quite important to understand the difference. On the one hand, I look at my life, as like taking physics and all and mathematics and all of this stuff pretty seriously, and just trying to do like serious work in that in the arena, building actual useful AI systems. That's kind of bloody intellectually challenging work. But on the other hand, there's this orthogonal orthogonal spiritual components to it, right? And what I am trying to say is that I am not trying to change the way you think about the world and how you find meaning, and that making all those choices, all of this stuff is extremely useful and valid, and that is the point in so many different ways. But among all the functions of the mind, there is a function of the mind that manifests itself when you learn how to let go of all the choice and become completely bias free, and just simply learn to observe what is it like when for the universe to prompt you, instead of you trying to impose your will on the universe, right? And that thing is not just a mental state, right? It's actually a physical relationship with the world. There's a changing in how you're being bound to the world that happens as a result of acquiring that view. So what I am trying to say is that if I can using words, so tokens, images, equations, whatever, any kind of tokens I have at my disposal, if I can transfer this concept into your head and it unfolds in your head, the nature of the binding of you as an agent to reality, your alignment with the quantum frame of the universe will substantially change, and it is provably for the better.
Yeah,
That is the idea that I'm trying to convey.
yeah. So you're not just you're not just trying to choose tokens. You're trying to choose a set of tokens that make sense to other observers so that you can explain your model, right?
Exactly. I'm trying to help. I'm trying to give you guys tools so that you can create models of what is it that I am trying to tell you that I am seeing, so that you can appreciate what is it that I'm trying to point out that is going on here. So I'm trying, you have to understand how my model is constructed in order to understand the model. You can't understand the model itself because it's the construction it's a dynamic object. It's a quantum state. Literally, what I'm trying to do is to copy a quantum state into your heads.
We're all just networks of wormholes, and we all have our fingers in each other's brains right now.
Right.
Yeah, and but this is how Buddha knew. Like when someone achieves enlightenment, you know that you're enlightened, and you know everybody else who is enlightened because it's an identity function. You simply know that we are the same quantum state. We're evolving together.
You wake up.
It's like, you wake up. I'm basically a different wormhole, and I'm here to minimize free energy around me in the way that is the most meaningful for me. So it's not like I can steal your story by telling you mine.
Right.
In somewhere in my story, you will simply find a part that is meaningful to you, and you're gonna say like, "Hey, Krzysztof, there is this part you haven't considered." I'm gonna be like, "Oh my God, this is amazing." I would have never saw that coming because my basis is different to yours, and that's how novelty is produced by basically choosing a different point of view. So I, as the universe, project myself into myself and have one point of view, and project myself into another point of view that's Max, and have a different point of view. And it's important for us not to have access to each other's points of view because that's what it feels like to have a point of view that is different. It's not clear how you can have a quantum structure that is the same and different at the same time. That is the thing I think that we're trying to figure out, essentially, how to effectively compress information in such a way that we're creating these interfaces between each other that are conducive to shared understanding.
We have, unless we had our shared theory with like human theory, for two models share the same state to break if you're putting them in line with each other. Like the way I'm thinking of it is like if what you have is a through line of states externally and a model where agent could hook into that through line and they could both be in it at the same time. They could share this state, but we can't.
Yeah, so you have to create a protocol between you and somebody else. What it means to share state, right? Because what it essentially means is that like in programming, you typically have a mutex. So we simply have we always outsource it to somebody else and say like, well, here's a guy who's gonna work as a guard. But imagine that you're just simply two physical processes and you want to share some state. Then you have to establish a communication protocol where my quantum sampling of the binding between the shared state, right, doesn't disturb the shared state. But we know that you can't sample and not disturb the state because all observation is interfering with the state. This is only possible if we're perfectly aligned and whatever I'm sampling is already what I expect there to be.
Observation or measurement?
It's the same thing, right?
Maybe, because some things are measurements and some things aren't. Isn't that the measurement problem?
I think that's just a matter of perspective. You always run into this question of like, well, who's ultimately looking?
Mm-hmm.
I've got the bounce, but like I just want to highlight this one thing. What I'm trying to point out is a little bit different than what the language I'm using to point it out. What I'm trying to point out is that there's simply a dimension of reality that you can learn to perceive that gives rise to the development of a new sense that is similar to sight, but is more related to spatial relationships in higher dimensions. And that is available to anybody And it's just something that you can develop as a matter of training, and that can be explained using the frameworks of science, why it's there and why it has to be there. So
You-
that's what I'm trying to say.
You are basically a shoggoth of wormholes, and with exercise, you can reach them out into the universe, right? Like you can extend them and set up communication with other shoggoths.
Yeah, you can flip yourself inside out and go and hang out in the other space. That's what liberation is. And there's a reason there, and there's even a really good reason why it's so hard to achieve it today. You know, the fact that there are 8 billion of us and there are like, what, 50 million at the time of Buddha, you know, that has to have some impact, right?
Yeah.
Leave these stupid
It's just,
systems and
I
get
actually, yeah, I have to go, but yes, I have to end the space in a minute, but thank you everyone so much for coming. I think this was an amazing conversation actually, and gonna keep doing this and continue on through the book. I actually think we made some good progress through the book today, and then we also talked about a lot of other really awesome things. So I guess just to close out, just a note on this topic that we've been kind of orbiting around, this topic of choice, and and I had my own kind of view on that, and there were other views, but I guess I'll take the last word here and just kind of reiterate my own perspective that so Peter Shor said, Peter Shor, of course, the guy who came up with Shor's algorithm, which is the reason why everyone is so afraid that quantum computing is going to break all of our cryptography, right? Peter Shor said, why not be a many worlder on Monday, a Bohemian on Tuesday, a Copenhagenist on Wednesday, if that's what helps you prove new theorems. And I think that was, when I first read that quote, I was like, what the hell is he talking about? Like only one of those things could really be right. You can't be all those things. But now after going through grad school and working in physics and improving a lot of, theorems, I think there's a lot of wisdom to that in that, when you're working on these things and improving theorems and doing physics, that's actually a very nice perspective to have, that you make choices, but you don't have to make the same choice every time. Right. And I think that Christoph was talking about kind of this perspective, and he related it to Buddhism and etc. And maybe you could think of it as like kind of the beginner's mind, at least in my simplistic interpretation of it. And I think it has to do with always make choices. You're always making choices, but you don't have to be particularly married to those choices you make. So I guess I'll close out with, choose a gauge, make commitments, and turn coffee into theorems, right? So anyway, thank you everyone for coming, and I hope to see you guys in the future, and I'll be hosting more of these. So see you all later.
Thanks, Max.
Thanks, man. That was great.
Peace out.